So, hello everyone. We'll start today's session. And because in the last lecture we have something not covered yet, but that part is a bit minor. So we'll put it in some of the week's third hour instead of covering that remaining things at the beginning of this week. Okay. Now, I believe that you have already seen the assignment released, the first assignment. Okay. Now, remember the due date will be the original week 7, which means the current week 8. Okay. So, remember to finish the assignment on time. So, by the way, I remember that some students asked me about some clarification questions about this assignment. So basically, you can judge by yourself. All right. So when you see that when you find that maybe something's missing, then just try to accommodate that by discussing some possibilities. All right. So this is the things I would like to share. Yeah. So please mute yourself if you didn't do that yet. So when you, yeah, thank you. Okay. So now we'll be, so you can see my full screen slide, right? Okay. Yeah. So so basically, in the first 4 weeks, we talk about the algorithm analysis, right, including online algorithm, approximation algorithm, randomized algorithm, and well, various other algorithms. And now, from this week on, we will start a new chapter and a new big category of topics called game theory. And actually, this is also, I believe, many of you are more interested in. All right. Okay. So we will start with the game theory basics, and then also by starting with some brief history. Okay, so this is well, the early days of game theory. In 1913, Zermelo provides the first theorem of game theory, and it shows that chess is strictly determined. And then 1928, John von Neumann proves the minimax theorem, and later, 16 years later, he and Oscar Morgenstern wrote the theory of games and economic behavior. All right, so I know that many of you know that von Neumann is considered to be a computer scientist too, right? But at the same time, he also the founder of the game theory in some sense, right? And then in 1950 to 1953, John Nash describes the Nash equilibrium. So actually, Nash equilibrium is the building pillar of the game theory. And actually, in this lecture, we'll also talk about this at the very beginning of this lecture. Okay. And then game theory actually assumes something. All right. Otherwise, basically, nothing can be done. All right. So the assumptions are humans are rational beings. All right. So they are always trying to seek the best alternative in a set of possible choices. Now, the reason we assume rationality is that we want to narrow down the possibilities of choices of different people, all right, and also increase the predictability of the outcome of the whole game. All right. Otherwise, well, if the people involved in the game can play in an arbitrary way, then basically there is nothing you can do. Right. So which strategy you will follow? Well, it's very difficult to figure out. Right. And then in order to characterize this kind of rationality, then we need to use the utility theory. So utility theory is basically saying that every participant in the game, he has some gain based on his choice of strategy and others' choices of strategies, right? Okay, and then this utility usually is not a linear function of the income or wealth. It can be somehow concave or convex or any reasonable function. All right, and basically it tells you a person's preferences with respect to the objects. Okay, so we assume that everyone wants to maximize his or her own utility. Okay, and then what is game theory? Well, game theory, in short, we can consider it to be a study of how to mathematically determine the best strategy for given conditions in order to optimize the outcome. Okay, now we have different types of games which we will introduce very soon, but for now, just bear in mind that we are trying to use mathematics, right, to compute some good strategy under some conditions, right? And then the purpose and the methodology adopted in game theory will be to find acceptable strategies in the conflicting situations, all right? And then these acceptable strategies may not be optimal sometimes. And then it is also trying to abstract the real complex situation, all right? Sometimes some assumptions will be made to make the model simpler. And as we mentioned earlier, game theory is highly mathematical. Now, but although it's highly mathematical, still there are some subclasses of game theory which involves light math. Okay, so not very complicated mathematics. And then, as we said also earlier, that the game theory will assume that all human interactions can be understood and navigated by the presumptions. Okay, now before we learn game theory, the first question we have in mind is why do we need to learn it, right? Or why is game theory important? Now, the reason to study game theory is that we are living in a world where at any time we are making decisions and there are many people, right? So they are just acting on their own. And then how to model this complicated interaction among individuals, right? So basically, we sometimes need to rely on the AI, all right, to figure out or compute or perform these tasks. And then actually, game theory, the most famous application of the game theory is to design the computer AI for chess or some other games played by two persons, right? And then AI, if you adopt a good strategy, right, and then it can be very competitive compared to the human experts, right? So I believe that you have heard about all the stories about how the computer AI like AlphaGo or AlphaZero beats the human experts in chess, right? Okay. Now, now the other thing game theory can help us is to analyze situations more rationally and formulate an acceptable alternative with respect to different circumstances. And then it can also be useful in modeling strategic decision making, including two categories. The one is games against opponents, right? So people competing with each other. And also, there are also some games against the nature, all right? So later on, you will see some game, there is a special role called nature, all right? So nature is trying to select something, right, as the input. And then in the end, the game theory can provide the structured insight into the value of information. Okay, so when you have certain kind of information, you will make some decision, and this decision, you can use the mathematical proofs to show that this is actually best. Okay. Now we start with the most commonly studied form of games called normal form games. All right. So in normal form games, we have a player set which has start from 1 to n, right? And then each player I has a strategy set. Okay, so the strategy set is called Si, and then we have Sij being the J strategy for player I. Okay, so let me use the laser pointer. Okay, so Sij, right, the J strategy for player I. And then here we assume that the players are playing pure strategy, which means that it's kind of fixed. Okay, so it's deterministic. All right, so under a certain condition, the player will always choose strategy 2. All right, so this is a kind of deterministic strategy, right, or we call pure strategy. And then the player I can choose from his strategy set, and then the set of profiles of strategies of all the players is represented as a Cartesian product. So Cartesian product just means that every player has a strategy set, and you cross these together, right? So it will be let me change it to pen. Okay, so it's something like S1 cross S2, etc. Okay, so it's a Cartesian product, right? every combination of strategies are possible. Okay, and the whole thing we denote it as S. Right? And then player I also has a gain function called GI, and then this gain function will give the player's gain for a strategy Sij. Now, of course, this is not a complete picture because a player's utility or gain, it also depends on how others choose their strategies, right? So the input to the GI function is not only the player I's strategy, it also includes other people's strategy. You will see very soon in the next page. All right. Okay. So you see that actually the strategy set is some the GI function is something like this. Right? Okay. And then you see that when you fix the strategy of each player, and then you have a gain, and then some strategy is called dominant or weakly dominant if this following inequality holds. So what does equality say? So basically it says that if everyone else's strategy is fixed, and then for player I, if he chooses Sij, the gain is always no worse than compared to when he chooses strategy L. Okay, so you see J is the strategy he chose now. Okay, this is J, right? It says, okay, I choose J, it is always no worse compared to when I choose L. And then the Sij strategy, we call it dominant. So basically, if you are player I, you will definitely choose the strategy J, right? Sij, because choosing Sij, well, somehow weakly dominates all the other choices. So of course you will choose the strategy Sij in this case, right? Okay. Now, if this inequality is strict, in other words, choosing J is strictly better than choosing strategy L, any other strategy L, then we say it is strictly dominant strategy for player I. So basically, at that time, there are no ties, right? No other strategy has the same effect as this strategy. This strategy totally dominates all the other ones, right? So in this case, we say Sij is strictly dominant strategy. Okay. Now, next one, we'll explain some further concepts called Pareto dominance and Pareto optimality. Okay. Now, suppose we have two strategy profiles. One is S, the other is T. Okay. And then when do we say strategy profile dominates the other or Pareto dominates the other? So here is the definition. So Pareto dominates, it says that if for agent I, all right, for agent I, GIS is always no less than GIT, then we say this is, well, in some sense, Pareto dominates the other strategy. Now, remember that this need to be true for every I, all right? So for every agent, all right, for every agent, the strategy profile S is somehow better than strategy profile T, right? So in this case, we say it is Pareto dominant relationship. Now, remember that you can raise questions anytime during the lecture if you are unclear about some concepts. Now, I want to share with you one thing. Actually, this subject will be somehow easier than the earlier 4 weeks. Yeah, so Xing asked, S and T are vectors. Yes, S and T's are strategy profiles, which consists of strategy for each player. All right, remember the G function? Remember the G function earlier? We have this one, right? So G function will take as input, well, this many, right? This many entries. So basically the strategy profile is a combination of strategies from all the players. All right. Okay. So this is the Pareto dominates. Now, one other thing, if this inequality holds for all the I, at the same time, it is strict for at least one J, then we say S Pareto dominates T. Okay, so this is a difference, right? In the above, it's a weakly Pareto dominates, which means, well, I'm roughly better than you, right? Well, so but it could be this. It could be the case that in every dimension I'm the same as you, so we still call it's weakly Pareto dominance. But if you say I have at least one dimension, strictly better than the other one, then I will Pareto dominate that other strategy profile. Okay. Now, one further strengthening effect. So if every inequality is strict, then we say T is strongly Pareto dominated by S. Okay, so now we have a strongly. So basically we have weakly and then no anything, nothing ahead, right? And then the other one is strongly. So you need to know the difference between these three definitions. Okay, now this one is a bit tricky. All right, so we say T is Pareto optimal if for all the other strategy profile, T is weakly T is weakly dominated by S, then every entry is the same. Okay, so what does it mean? So it means that if somebody can Pareto dominate or can weakly Pareto dominate you, then you force it to be the same, right? So nobody else can be very well, can have something like one entry larger than you, the other entry equal to you, right? So nobody else can do this. If they can somehow weakly Pareto dominate you, then they have the same entry as you in every dimension. In this case, we say you are the Pareto optimal. So we know that well. So I just ask. I guess I will ask one question about. Do you know the Pareto optimal definition? Not in game theory, okay? Not in game theory. Do you know the Pareto definition, Pareto optimal definition for comparison of different vectors? Oh, okay. So that, thank you. So then I guess I need to explain a bit about what is Pareto, okay? So let me just explain. Okay, so when I draw a two-dimensional vector, okay, so this is an axis. So you see that you can draw many points, right? You have a point here, you have a point here, and then you have a point here. Okay. Now, so what is so let me draw three more things. Okay. So I have 5 points here. All right. And then our objective is to maximize every dimension. All right. So remember these points. Every point has two entries, right? Two coordinates, right? For example, some points are 4, 6, right? So basically, our purpose is to maximize each dimension. All right, maximize each dimension. And then what is what is the Pareto optimal solution in the figure I draw here? Now, actually, it also will answer Xinran's question. Okay, so in the figure I draw here, what does it mean by Pareto optimal? Pareto optimal means nobody else can dominate me in both dimensions. Okay, so for example, I'm 4, 6. If there is a 10, 20, then 4, 6 is not Pareto optimal because there is another person which can dominate me in both dimensions. Okay, but on the other hand, in the figure I draw here, according to what I just explained, how many Pareto optimal solutions can you find? Remember, we are trying to maximize, okay? Yeah, I know that many of you are, well, very quick in thinking. So remember, we are trying to maximize the values of the points, okay? Okay, very good. 3. Yeah, that's right. So basically, this point, and this point, okay? These 3 points on the upper right, they are Pareto optimal because for each of them, for example, this person, nobody can dominate him in the y-axis, right? Because he has the largest y-axis value, right? Y value. So nobody can dominate him in y. Therefore, well, we say that if somebody dominates you, that means he need to be larger than you in every dimension, right? Okay. So if this cannot be happening, then you are Pareto optimal, right? Now similar issues here, right? So this has the largest x, so of course nobody can dominate. Now this one is also Pareto optimal. The reason is, well, you see that it does not have the largest x, but the only point that can be larger than him in x is this one, right? But this one has smaller y, so this one cannot dominate the square, right? Okay, so in this figure, right? In this figure, you know that, well, we have 3 Pareto optimal solution, right? Okay, so yeah, let me just bother you once to see whether you understand Pareto optimal now. Oh, good. Okay, majority understood. Yeah, that's good. Now, yeah, so I will close the uh, poll. Yeah, then we will have similar reasoning for Pareto optimal, Pareto domination for strategy profile. So you see that here, right? We say that we have 2 strategy profile, right? 2 possible strategy combination, and then we say T is Pareto optimal. If somebody want to weakly Pareto dominate me, then he or she must be the same as me in every dimension. Okay, so that means, well, he cannot have strict advantage over me in any dimension, right? And if that's the case, we say it's Pareto optimal. Okay. Now, another thing, we have weakly Pareto optimal. So weakly Pareto optimal means it's a bit weaker. Weaker. The reason is, well, nobody can dominate me in every dimension. Okay, it's okay that he dominates me in some dimension, right? Equal to me in some others. That's fine. That's still fine. I'm still weakly Pareto optimal. But if somebody can dominate me in every dimension, then it's no good. You are no longer weakly Pareto optimal. Okay. Let me answer 2 questions. If a strategy profile is Pareto optimal, then every agent chooses dominant strategy. Well, this yeah. So this question is very well. It's not easy to answer. Okay, because dominant strategy has a another definition. Yeah, so dominant strategy says that if you choose this strategy, your utility or your gain is well, at least the is at least as much as when you choose other strategies, right? Okay, so but it may not be true that in this case everyone chooses dominant strategy, because it could be the case that um, this T is weaker, or this T is somehow dominated by one dimension. In one dimension, for example, agent K in dimension K is dominated by the other strategy profile. But in if that happens, then for the other dimensions, then probably it's well, this T can somehow be better than the others, right? So if the T can be better than the others in some dimensions, then it will be somewhat safe, right? When we talk about the Pareto domination. Okay, yeah, thank you. It's good to understand. And then the Jiang Kun asked, so the example is weakly Pareto optimal. Which example? You mean this example? The example I draw here? Okay. Let me see. Yeah. So for these, right? For this one is actually not weakly. It's weakly Pareto optimal, but it's also Pareto optimal. All right, because Pareto optimal says if somebody can dominate me in every dimension, they have to be the same as me in every dimension. But here, for these 3 points, nobody can dominate them in every dimension, right? So it's Pareto optimal, not only weakly Pareto optimal. Okay. Yeah. So any other questions? Okay. So if this is the case, let me. Yeah, so there's one other question. It seems the weekly optimal is not strong. You mean weekly Pareto optimal, right? Yeah, weekly Pareto optimal is weaker than Pareto optimal. So weekly Pareto optimal, I can draw another figure. For example, I have another point here. Okay, I have another point here. And then this one is still weakly Pareto optimal. Why? Because even though this newly added point can dominate this in every dimension, but in one dimension it's equal, right? It cannot be, it's not larger, right? So only if somebody is here, right, then weekly Pareto optimal will be broken. But if there's only somebody here, no worry. Okay. So Xinan, did you understand this point now? If only somebody is the same as you in some dimension, larger than you in other dimensions, that's fine. That's still weakly Pareto optimal. Okay, good. All right. Okay. Yeah, so weak or strong only defines yeah, so weak or strong, the main differentiation happens about the whether it can be dominated in each dimension, right? So weak says you only need to dominate me in one dimension, then I'm no longer Pareto optimal. But strong says you have to dominate me every dimension, right? Okay, good. Yeah, so this is the Pareto optimal definition. Now let's move on. Now we come to Nash equilibrium. Okay. Now, what is equilibrium? Equilibrium says it's a solution. It's a stable solution where no player has any incentive to deviate from his current strategy. Now, of course, there is a condition. The condition is other players do not change. Okay. So now you see that, for example, you have 100 people in the group. Everyone makes one choice, right? And then say, okay, if I'm one of them, and then for the other 99, if they fix their strategy, and then if I can change my strategy, then I will not change because my current strategy is the best. And in this case, that's okay, good, right? I will not move. If others do not move, I will not move, right? And then what's the strategy? What's the stable solution? The stable solution says if you fix any of the remaining group of agents, then the focus agent you are looking at, it will not change its decision. And then you see, if others do not change, I will not change. And this happens for every agent or every player. Then we say this solution is stable, or this solution is a Nash equilibrium. Okay. Okay, so I guess this is well, somehow easier to understand, right? So just look at from the angle of every player, right? And you tell him, okay, these are all what others chooses, right? What others choose, okay? And he asks you, will you make a change in your strategy? And then you compare the outcome of all the GI function, GI value. They say, okay, I will not change. I think my current one is the best. And then if everyone thinks so, then it is a Nash equilibrium. Okay. Now let me just well bother you again. Is the Nash equilibrium concept okay? Yeah. So can you, well, at least on a high level, right? You know what Nash equilibrium means. Nobody will change their choice if others do not change. Okay, the majority understands. There are still some who do not understand. Well, you will see more clearly if I give you one example, or maybe, well, I'll give you more examples later on. Don't worry. Okay, so basically for now, the story is you have many people, each of them choosing one strategy, and then if nobody will change their strategy, given others' strategy is fixed. Okay, so others are already fixed, and then you say, okay, I will not change. If everyone thinks so, then it's a Nash equilibrium. But if there's one person who do not think so, then what will he do? Well, here comes the so-called best response. Okay, what does that mean? It means that if I fix the strategies of other players, all right, if I fix the strategy for other players, and then if I choose L, if I choose L, then this will not happen. Okay, so what does it mean? It means that, well, if I'm not happy with my current solution, I will deviate, right? I will change to another strategy. Now, I will change to what strategy? I will change to the strategy which gives me the best GI, all right? The largest GI. This is called best response strategy. Okay, so in other words, here, right, J, right? This J is larger than any possible L decision, right? L is strategy L. Then we say, okay, for the agent I, choosing J is best because in the current situation, right, he gets the most out of the game, right? Okay, yeah, so Xinran, you're right. It's the local maximum, right? Not minimum. The local maximum of GI when other dimensions are fixed. Okay. So because we are trying to maximize the utility, so therefore we are trying to get a bigger GI, right? And therefore we try to choose a J which is better than any other choices. All right, so this is the best response strategy. Now, if there is exactly one such strategy as IJ, then his or her strictly best response strategy to the other players. So this is this is a bit wrong. Okay, so it's not S minus I. So it's minus I should be subscript. Okay, so here we have something to share. So what does the minus I mean? Minus I means the strategy chosen by a people or players not equal to I. Okay, so we have a player I, and we also have players other than I, right? So minus I means players other than I, their strategies. Okay, so this is something often used in the game theory background. Okay, now, okay, so then how to define Nash equivalent? So more formally, all right. So a strategy profile S is a Nash equivalent if the strategy chosen by agent I, which is J, right? Sij, right? This is a strategy chosen by agent I. This strategy is the best response strategy for player I. So in other words, everyone is choosing his best response based on the current choices of other people. So in that case, definitely nobody will deviate because everyone is already getting his best utility or choosing his best response strategy. And then nobody will deviate, right? Okay. And then one further thing. If there's only one such strategy profile S, then S will be called in a strict Nash equivalent in pure strategies. Okay. Now, because for different games, sometimes there may be more than one Nash equivalent. Well, a lot sometimes. So if there's a unique one, then we say it's a strict Nash equivalent. All right. And then this Nash equivalent actually also has something to do with the local optimal or global optimal thing. So later on we'll see. All right. So very soon. Okay. So now here is the relationship between different concepts we learned up to now. Now we know that well, Pareto optimal strategy will imply weakly Pareto optimal strategy, right? It can be deduced. And then here we have a dominant strategy. Okay. Now, so we know that strictly dominant strategies will, so if everyone chooses strictly dominant strategy, then definitely it's a Nash equilibrium, right? Because no doubt, right? So this one can imply Nash equilibrium pure strategy. Very easy, right? And also strictly dominant strategy can imply dominant strategy because dominant strategy is a bit weaker, right? And then also strictly dominant strategy can imply strict Nash equilibrium in pure strategy, which means if it's a strictly dominant strategy, that means it's a unique one, right? Single strategy which is best for so for each of the players there is a single best strategy, and then if everyone choose that, then of course there's only one such profile, right? everyone chooses the best, then it's a unique one, and it will imply strict Nash equilibrium in pure strategies, right? Okay, so these are the relationship to help you understand those concepts. Now, basically, these relationships, the major thing is about those larger than or larger than equal to. Okay, so when you play around with these relations, right, inequalities, then you will get these different concepts. Okay, but well, these I would not need you to remember it. Okay, because the purpose of the course is not to remember things, it's to understand things. So these concepts have very intricate difference. So if I would ever ask you questions in this, it will be open book. Okay, if it's closed book, I would not ask you questions about the intricate difference of different terminologies. Okay, especially this part. Okay, so now let's come to the schedule of the whole remaining 8 weeks or 9 weeks of this course. Now, basically, we will be talking about algorithmic game theory. And because we are CS students, right, we are not economics students, so we are talking about algorithmic game theory. And in some scenarios, we also call it computational game theory. So these two have some overlap, all right? So algorithmic game theory is more mathematical. Computational game theory is also mathematical, but sometimes there will be some other possibilities. Okay. Now, in this lecture, we will talk about mainly two things, but of course there are more to cover other than these two. So we'll talk about the inefficiency of equilibrium. In other words, this is about well, Nash equilibrium is good. Nobody will deviate, but sometimes it will give you a solution which is very bad in terms of social welfare. Okay, in terms of a global society, it's not good. So we'll try to measure how inefficient it can be, right? So this is about inefficiency of equilibrium. And then the other thing we'll talk about is the complexity of finding equilibrium, because there are some theorems by Nash saying that, well, in all the situations, some equilibrium always exists. But always exists does not mean that you can compute it very easily, because for CS, for computer science, we care about how fast we can get such a solution, right? And then just like we have a P problem and NP hard problem, right? So for NP hard problems, for now, we don't know how to quickly compute the solution, right? So that's the major focus of our CS students, right? Okay, and then in the remaining lectures, we'll talk about market equilibrium, including matching, auction, and other settings. And also we'll talk about the scenario of multi-agent systems, where we have many interesting problems, including fair division or scheduling, and these will all involve multiple agents in the society. And then for algorithmic mechanism design, we'll mainly talk about facility location games, which is also one of my research directions. Okay, and mechanism design just says that you try to design an algorithm which can guarantee that nobody participating in the game will ever cheat on its information. Okay, we care about the truthfulness. Everybody tells the truth. We hope that everyone can tell the truth, right? And then finally, there's also a big domain called computational social choice. This is a broader field. Well, we'll probably cover some. Okay. Yeah. So then we will start with the inefficiency of equilibria we mentioned earlier. What is that? Okay. So there are two concepts: price of anarchy and price of stability. So price of anarchy. So this one means no government. All right. So in other words, everyone just act on its own. There is no regulation. All right. So if there's no regulation, then what's the worst Nash equilibrium will give us? So because we know that in the society, right, if everyone acts on its own, then he always chooses the best for himself or herself, and then the whole system will evolve, right? So player one changes his strategy, it become better for him or her, and then player two changes, and then after many rounds of changes, at some point you reach a Nash equilibrium where nobody will change. So when that happens, you have a cost of that Nash equilibrium, right? And this cost, we hope it to be small, but because we have no regulation, so it can be very bad, it can be very big, right? So compared to the optimal solution, So optimal means what? Optimal means with the government controlling everything, and then you see that I asked player one, you must choose this strategy. Player two, you must choose that strategy. So if it nominates everyone to choose a specific strategy, I can achieve a socially best cost. So cost function, optimal solution can minimize the cost function, right? So this is a cost of OPT. But Nash equilibrium solution, the cost can be very big, and the POA is measuring how bad Nash solution can give you. All right, so it's the maximum of the ratio of Nash solution and the optimal solution. The reason we need to take a max is that there can be many Nash equilibrium solution, right? Okay, so we'll focus on the worst one. Okay, so this is called POA, all right, price of anarchy. How bad a Nash equilibrium solution can be compared to the optimal solution. Now the other one is called price of stability. The price of stability says how good a Nash equilibrium can be. All right. So the only difference compared to POA is that you change max to min. All right. So we still divide Nash cost by the optimal cost, right? But this time we are somehow being very optimistic. We think that the system is trying to evolve into the best Nash equilibrium, and then let's see how good it can be. So it may be as good as OPT, and in this case, the POS is 1, right? Now it can also, you can also possibly show that maybe it can never be as good as OPT. Then POS will be a value larger than 1, right? Okay, so well, now let me do a polling. Are you fine with the definition of POA and the POS? Okay. Yeah, so the same percentage. All right, the majority understand. Okay, so if you didn't understand yet, again, as I promised, you will see some well, examples later on. Now, because now we are talking about abstract concepts, but later on you will see how to really interpret different scenarios using these POA and POS concepts. So for now, you just need to know, well, price of anarchy means how bad a Nash equilibrium solution can be compared to the optimal solution. And then price of stability means how good a Nash equilibrium solution can be compared to the optimal solution. Now, actually, you are encouraged to raise the question in chat if you didn't catch the concept, so that I can know what the question is, right? What the problem is. Now, for now, I will temporarily move on. Okay. Now, of course, this price of anarchy and price of stability, well, this is something that you need to memorize. Okay, this is not something very intricately defined. It's very well easy to figure out. Okay, so now let's talk about the hardness of computing Nash equilibrium. How hard is that? Okay, now for games, there are different types of games. All right, so in normal form games, there is one special category called zero-sum game. All right, so zero-sum game. Let me find the cursor. So what does zero-sum game means? Zero-sum games means that two players play with each other. If player one get a benefit of 5, then player 2 will lose 5. So basically, the benefit of player 1 is 5, then the benefit of player 2 will be -5. They add up to 0. So it's always true, no matter what kind of strategies you chose, as long as one of them get K, the other one will get -K. Okay, so this is zero-sum game. Okay, now because each player is trying to minimize the maximum gain of the other player and maximize his own, right? And the computation of Nash equilibrium can be transformed to a minimax strategy problem, and then it becomes a linear program, and then it's solved in polynomial time. Now I will not talk about details. These are relatively easier. Now the more challenging thing is about what? Is about the general normal form game, which means it's not zero sum. Okay, so if player 1 get 5, player 2 can get -1. All right, does not always add up to 0. Okay, so this game, is it easy to compute? Well, it's not. So here there is a special complexity class called TPAD complete. Now it's just like NP complete, but not the same. Okay, so NP complete, now you already know, right? NP complete means it's the most difficult question in the, well, in the class of NP, right? Everybody else can be solved if you are able to solve a NP complete problem, right? So every other problem in the NP category can be solved if you are able to solve an NP complete problem in polynomial time. So this is NP complete. So here we have another definition called PPAD complete. Oh, it's a bit long, but here I will tell you the general story about PPID complete. So the full name is polynomial parity argument for directed graph, or end of the line problem. So what is this? Well, we have a scenario where you have a graph G. Okay, it's a very large graph, possibly exponentially large. Okay, so remember, usually we say the graph, if it is given to you, it is polynomial size, but here it's different. The graph itself is exponentially large. Okay, and then it guarantees that there are no isolated vertices, and then every vertex only has one predecessor and one successor, which means every node only at most has a degree in degree 1, right, and out degree 1. Okay, it's very easy. Everyone is just at most degree 2, one in, one out, or nobody in, one out, or one in, nobody out, or well, so it cannot be isolated. So only these three cases, right? Okay, and then so we can do something. All right, so we say that the G is exponentially large. Then it's a bit challenging to know the whole picture of G, right? But you can do some special action. You can call some function fv. All right, so you can call some function fv, and this fv will return you the predecessor and successor of a certain vertex v. Okay, so if I can make a query, ask you, can you tell me who are the neighbors of this node? Okay, then the fv tells you, okay, this node u is your incoming neighbor, and this node w is your outgoing neighbor. Okay, so I will tell you these two parameters. Okay, well, so now what's the task? So the task is, I will give you a vertex s with no predecessor, which means I will give you a node where nobody else points to it, right? It's a starting node, right? It's a source, right? You can consider it as a source. And then I also give you the function fv. Then I ask you, please find a vertex t, which is not the same as s, right? Such that this t is somehow the end of line, all right? No, from t, it goes out to nowhere, or there are nobody going into t. Okay, so yeah, so up to now, I'm only giving you some abstract explanation. And then as usual, I will quote, or I will raise a poll to see how many of you understand the problem. Okay, I give you a source. You can do queries, and then please find another source or another sink. Oh, good. Very nice. Okay. Okay. Yeah, so I can see a majority or weakly majority of you understand this problem. Then I believe that after I explain the next one, it will be easier, even easier to understand. Now, this problem, as I mentioned, it's a PPAD complete, right? And then this problem actually could be solved using a reduction from a very famous Sperner lemma. Okay, so this is a very interesting thing. In my undergrad study, I didn't have the chance to learn it, but in my PhD, I have the chance to learn it. It's really beautiful. So this figure, actually, well, let me talk about Sperner lemma first. Okay, forget about these arrows. So what's a Sperner lemma? Sperner lemma says I have three colors or three labels. All right, you have a triangle, and this triangle is split into many small triangles in this way. Now, this is easy, right? And then I tell you, I will label the three vertices of this triangle, the big triangle, as 0, 1, 2. Okay, 0, 1, 2. And then for all the small breakpoints like this, right? All the small breakpoints like this, and then we just check which edge this breakpoint is on. All right. If it's on the edge 0, 1, then you can either assign 1 or 0 to those small dots. Okay, so you see that here in this example, we assign this one to 1. This is also 1. This is 0. This is 1, right? So basically, on every edge, the smaller breakpoints, they can only get labels of their endpoints. Okay, so the bottom edge can only get 0, 1. And then how about this edge? This edge can only get 1, 2. Okay, and then this edge can only get what? 0, 2, right? Okay, and then all the inside, I don't care. All right, the inside nodes, just up to you. Okay, you can cut, you can label them in your, well, in an arbitrary way. Okay, I have no restriction at all. Okay, well, so now, this one is very important. So that's why I would like to see whether everyone understands the label. Okay, how we label the breakpoints. Is it clear? You have 3 vertices. Oh, it's not clear. Okay, so let me just explain again. Okay. Okay, let me finish the poll. So, so basically, you see. So no. Before I explain how we label, let me ask one more question. Are you clear about how we divide a triangle? Okay, dividing triangle is also not clear. Okay, so that's why you cannot know the label. So basically, you can consider the triangle is a regular triangle. Okay, and then every edge has a length k. Okay, every edge has length k, and then this breakpoint is integral point. Okay, you can say this is starting point, and then for every length 1, I mark another point. Every length 1, I mark another point, and so on. Okay. Now the other edge also length k. So again, as the first edge, it's every length 1, I mark a point. Every length 1, I mark a point. Okay, so it's the same for the bottom edge. Okay, every length 1, and then I connect all the breakpoints. Yeah, so in this case, k equals 5. You're right. In this case, in our example, k equals 5. So every edge, there are 4 breakpoints in the middle, right? 4 breakpoints in the middle. I will connect the breakpoints with lines parallel to the triangle edges. Okay, so in other words, here we have a horizontal connection, right? And the connection in this way, from upper left to lower right, and also connections from upper right to lower left, right? So it's a very, very regular split of the original triangle into many, many small triangles. Each small triangle has an edge length 1 for each side. Okay, so now, yeah, so the triangle is an equilateral triangle. Yes, you're right. Every edge has the same length. Okay, so now, is it okay about the splitting of the triangle? Is it clear now? Oh, great. So thank you. So after splitting, now the next thing is to color, right? The next thing is to color. Now the next thing is to color or label. Then we say, okay, after we have this very regular shape of the triangle tower, right? And then we say we assign label 0 to this vertex, right? So this is label 0, right? To this point, and then this is label 2, right? And this one is label 1. Okay. And then for every breakpoint, I also need to allocate a label. Now this time, the label you allocate to the breakpoints has to be the same as one of the endpoints on that side. For example, if we look at this side, you see this side, the endpoint has label 2 and 0. Then every breakpoint on the line on this edge will have a label 0 or 2. Then which one has 2, which one's of 0? Okay, it's your choice. I have no specific requirement. As long as you follow the rule, right? As long as you label them either as 0 or 2, then I'm happy. Okay, then the same thing happens for this, right? For this edge. This edge, the 2 endpoints label is 2 and 1. And then I ask you, oh, please label 1 or 2 for every breakpoint here. All right. Okay. Which one is 1? Which one is 2? I don't care. You can make them all 2 or all 1. I don't care. All right. As long as you follow my high level requirement, that's fine. Okay. And then for the bottom one, 0, 1, right? So you just say, okay, every breakpoint is either 0 or 1. Okay. And then now when you connect those breakpoints, and then you see in the middle there are also some crossing point, right? Like this one, there have many. You have quite some crossing point. So for crossing point, I do not have any restriction. You can label them as you wish. Okay. Well, so now let me see whether it's clear about label. So basically, you have the flexibility of labeling the triangle, but you have some restriction. The restriction I already told you, right? For on every edge, right? On every edge, the outside edge, the breakpoints can only share the label of the 2 extreme points, right? And then inside, I don't have any restriction. Okay, inside I don't have any restriction. Okay, good. So although there are still a few who don't understand, but I guess I will move on. And then after I explain the whole thing, we will take a 5 minutes break. Okay. So now, what's Spinner's lemma? Okay, Spinner's lemma says if you do this, then there is always a triangle somewhere in this big triangle. So there's always a small triangle. For example, this one. Okay, there is always a small triangle such that the 3 corners of the triangle have different labels, 0, 1, 2. They must all appear. So in this example, we have 3 such triangles, right? 1 here, 1 here, and 1 here. Okay? So this is Spinner's lemma. Okay, yeah, so I guess we can take 5 minutes break now and then think about it, all right? So how to show it, all right? Now actually we are not proving, we're not proving it, although proving itself, it may not be that difficult, but we are trying to show the connection between Spinner's lemma and the one we talked about earlier, about this one, end of line, right? Or this one. All right, so 5 minutes break. And you can ask questions during break too. Okay, we'll come back. Okay, midterm. Midterm, more information. Well, firstly, midterm will be online. This is something for sure, and it will be closed book. And then we'll use 2 devices to do invigilation. And then, well, so I will post the regulations on Canvas some 1 week before, maybe. Okay, basically, you need to set up a second device to record the whole thing, whole process. You take the midterm and upload to OneDrive. And then about scope. So I remember midterm is week 10. So basically, the scope would be the materials before week 10. Okay, so and yeah. So what other information would you need? Yes, I believe so. March 24. I need to check the calendar. It should be. Institute website. Ah, it's very strange. Well, anyway, If March 24 is the week 10, then it would not be March 24. Okay. This week's lesson. This week is week 6. Yeah, this week is week 6. Oh, okay. Shujin asking what happened for the contents we didn't finish in the last lecture. So we said that we'll cover it in some lecture where we have a remaining time in the third hour. Okay. So for this lecture, I do not see the possibility. So probably will postpone it a bit later because that part is somehow independent, not relating to the other materials in this course. So it's okay to postpone it. Okay, so I guess we can start. Let me go to the slide. Okay. Yeah, so coming back to this picture, right? Now, the first thing is what? The first thing is how to prove it, right? Now here we have some very interesting construction. This interesting construction allows us to compute to prove Spencer's lemma. At the same time, showing that actually getting the information of the sink is not that easy. Okay, so you see these many arrows, right? So what does the arrow mean? Can you guess? I already draw those arrows, right? So can anyone tell me what's the rule we are using to decide how your arrow cross every edge? Let me So any guess? Yeah, edge 0, 1, right? So only edge 0, 1, you will have edge, right? Okay, good. Then which direction? Bottom up. This is a bit abstract. Okay, yeah, the left 0, right 1. Yeah, very good. Okay, so basically you see that every edge, right? This this uh, this crossing, make sure that 0 is on the left, 1 is on the right, right? Okay, clear? So that's how we form these edges, right? For example, you have this edge, making sure 0 is on the left, 1 is on the right, and this is also right. 0 on the left, 1 on the right, etc. Right? Okay, so for all the other places you have no edge. For example, 1 1 no edge, 1 1 no edge, right? So only 0 1 have edge, and you make sure that when you draw that edge along the edge's direction, 0 is on the left of the edge and 1 is on the right of the edge. Okay, so by doing so, you are able to have a graph, right? So this graph you see we constructed, right? So you have some paths like this, and then you have some paths like this, and you have some paths inside like this, right? Okay, so now there's a claim. So the claim says what? Now, one thing, okay. Now, before I tell you the claim, do you think there's a cycle in the triangle? So in this, so there's a cycle you can find, like like this circling around. Is this possible? No, no, no. I see many no's. I see many no's. Really? Any second thought? Okay, so now you realize, well, actually it's possible. Why? Because if this is not 0, this is 1, then there is an edge like this, right? Okay, well, the cycle is possible, right? Cycle is possible. But one thing is not possible. So can one node have degree 3? For example, can a node in this such a graph have degree 3? 2 incoming, 1 outgoing. This time is no, right? Because for a triangle, you know, 3 sides. You can, the best case you can have is 1 0 2 2 1, right? Or 1 1 1 1 1 2 zeros. Now these two cases, both of them will only give you 2 edges, right? Just like this. You see that this triangle, you have 1 1 0. That's why you have 2 edges, 1 here and 1 here, right? Okay. Well, so you see that this graph, this new graph, right? New graph constructed on top of the triangle. This new graph, every vertex, it only has degree 2. And furthermore, these 2 degrees, one is in degree, the other is out degree. You cannot have the 2 arrows pointing together, right? You cannot have something like this point here and this point here. Will this happen? This will not happen, right? This will not happen. That's good, right? So you can see more properties, right, by looking at some triangles, right? Because the only triangle that allow you to do such kind of drawing is 2 kinds of triangles, right? One triangle is something like 0 1 1, right? The other one is 0 0 1, right? Only these 2 kind of triangles will allow you to draw some edges, right? And then when you make sure 0 is on one side, then the drawing will be like this, right? Okay, 0 on the left. And then for this one, 0 on the left, the drawing will be this, right? Okay, so you see that no matter which small triangle you have, when you draw these edges, they are always something. They always go from one side to the other. You never have any chance that the 2 edges just bump into each other. The arrows touch each other. Arrowheads touch each other. That's not possible. Okay, so that tells us the new graph you constructed consists of some cycles and some what? Line or path, right? Okay, yeah, very good. Okay, so you consist of a directed cycle or directed path, right? So just like this one, this is a path. Where's my cursor? Yeah, so this is a path, right? Okay, and this is also a path. Okay, well, good. So up to now, any question about how the new graph is constructed and what the new graph consists of? It consists of cycles and directed paths. Now, any question here? Now, if no question, I will leave the remaining question to you. Okay? So then how do you show that there is a triangle with 3 corners labeled as different colors? Now, actually, this is well, this one, as I said, I'm not trying to prove it. What we are trying to prove is the end of line, right? So I like Anyu said, right? We are trying to prove there's finding end of line is somehow hard, right? Or we try to link the end of line problem to the finding of a triangle with 3 different labels problem, right? Okay. Well, but of course, it would be good to know why there is such a so basically end of line, right? So if some line end up right in some triangle, that triangle must be what? Must be the triangle we are looking for, right? It must be a triangle sharing 3 labels. Why? You see, when you have an edge going inside a triangle, that means on the 2 sides of the edge, it's 0 and 1, right? And then it does not go out. Why it does not go out? Can anyone tell me? Why it does not go out? No 0 1 anymore, right? Because there are no 0 1 anymore, so that means that this vertex must be 2, right? Okay, so then you find a 0 1 2. Okay, well, so now the problem is can you prove there is always a so-called end of line inside the big triangle? In other words, there is an ending point of a path inside the triangle. How to show that? Yeah, the path cannot cross left side or right side. Very good. So you find the first point, right? The path basically can only go in from the bottom, go out from the bottom, right? Okay. Yeah, and then what's next? Okay. So Wing Chong said try every 0, 1. Okay. So actually this point is not difficult to find. Just yeah. Oh, very good. So Jian Cong, you will get 1 bonus. Okay. So Jian Cong said the entry is odd, which means when you go into the triangle from bottom, the 0, 1 entries are odd. Okay. Why? See, because only 0, 1, right? So the bottom edge is 0, 1. Inside you can label any 0, 1, 0, 1. But the only switching from 0 to 1 and then switching from 1 to 0 has a possible entry or going out, right? So for example, in this figure, you see switching from 0, 1, you have a edge going in, and then switching back from 1 to 0, you have an edge going out, right? And switching from 0 to 1 again, you go, well, sorry, you go up again, right? But remember, your final destination is 1. So you will switch for an odd number of times, right? So 0 to 1 once, 1 to 0 twice, 0 to 1 again 3 times. So basically, your target is 1. So along the way, you only switch an odd number of times. So in the bottom boundary, your arrows, right, going in or coming out, the count is odd, right? The count is odd. But for path, entry and what? Entry and going, starting and ending, right? So it's even count, right? Starting and ending, it's even count. So since the bottom level, it's odd count, it must be true that inside the triangle, there is some ending point. Or there's some starting point. Anyway, so if inside there's no starting or ending point, that's basically impossible, right? So that shows inside the big triangle, you have at least 1 ending point or 1 starting point. So is this fine? Now this is a bit tricky to understand, but I hope that the majority of you can get the point. So let me just do a query now. Do you get the argument? So because the high level graph, it consists of paths or cycles, right? So the endpoints, the count is even. The count of endpoints is even, right? And then you know that the starting point and ending point outside the triangle can only happen in the bottom edge, right? Because the other 2 edges is 0, 2 or 2, 1. No crossing. So only bottom edge can have any edge going in or some edge going out, right? Only bottom edge can do. But we argue that in the bottom edge, the entering or going out, this count is odd because only you switch from 0 to 1 or switch from 1 to 0, those switches will allow some edge going out or coming in, right? But you have 1, so your starting position is 0, ending position 1. Along the way, the number of switches you can have is always odd, right? Switch from 0 to 1, 1 to 0, 0 to 1, right? So it's always odd. So there are odd crossings or odd extreme points or starting points or ending points in the bottom boundary. And then because the total count is even, right? The total count is even. So you have an even number, say 10, okay? You have an even number minus an odd number, which crosses the bottom boundary. And so the remaining count inside should be 7, right? Okay, so remaining count inside is 7. No, you can have some paths like this. You can have some paths like this. Both entry and the exit is inside, so they will contribute a pair, right? This is a pair, and then well, after you remove those pairs, you still have one left, right? So that one must be single, right? It's by himself. Now it's either what? It's either entry, right, or endpoint. So that shows that inside that big triangle there must be one endpoint. Okay. Well, so I don't know whether after my second explanation, is it better? So now do you get the argument that there's at least one endpoint inside this big triangle? Yeah, it's good to see that better understanding now. Now, even though yeah, there's still someone who didn't get it, but that's fine. So basically, I'm trying to let you know, or trying to let you appreciate that actually this kind of proof is very intricate. Okay, so it uses a very how to say fundamental argument. Okay, the argument is not difficult, but it needs some thinking. Indeed, right? It needs some thinking. So if you still didn't get it, that's fine because this part is irrelevant to the topics we are going to introduce next. So if you still didn't understand, now try to dig deeper, right, after the class to see whether you can digest what we explained. Okay. All right. So actually, there are some questions. Oh, okay. So actually, there are some questions you raise. Some of you raised in the chat earlier. Um, so even just means double, right? So there's a kind of 4 2 6 8, right? So this is an even number. And then so the reason that we have even number of starting point or ending point is because the whole graph consists of directed paths or cycles, right? For cycles, no endpoints, and for paths, entry and exit, right? Okay. So well, so I guess so. For this one, we will just stop for a moment. We'll move on to some other basics of game theory. Okay, so this is about hardness of computing Nash equilibrium, the general normal form game. Okay, so now let's deal with some easy things. All right, so these are somehow more intuitive. All right, so as we mentioned very early back, there are different types of games, right? So there are sequential games, well, versus simultaneous moves. So what's sequential and simultaneous? Well, it's very easy to imagine, right? So sequential just means that everyone moves one by one, right? So simultaneous means okay, uh, all the people move at the same time. So for example, there are 3 players playing together, and then one of them says, okay, the other 2 they are taking this strategy. I would consider changing mine. Okay, so I change mine. But before I change mine, other 2 persons also see my strategy, right? So they will also change their decision. So all the 3 people change this decision at the same time. Okay, so this is called simultaneous moves. All right, sequential just means I change first, and then you change next, and then he or she changes in the third round. Okay, so this is sequential versus simultaneous. Okay, so you see this is a pretty easy concept, right? And sequential games, sometimes we can model it as extensive form game, um, especially so. I guess you in the undergrad study you have learned game tree, right? So basically the for Go or chess, players will play alternatively, right? I place my white color chess, and my opponent plays the black one, right? So black, white, just play alternatively. So this is sequential game, right? Okay. Now simultaneous game means so actually simultaneous game. One is what I mentioned earlier, right? But the other is another name for normal form game. So which means that you have a so-called payoff matrix, and then the game dynamics is one by one or at the same time. So here you see, in this simultaneous game, we not only handle everyone moves at the same time, but we also handle one by one. So also you can, well, starting from any status, you can allow one player to move first. All right. After he moves, then you ask the other player to move. Okay. I will give you some examples. So what's the payoff matrix? So payoff matrix is basically like this. You have player one, row side, or row player. Player two is a column player. All right. So player one has two strategies, A and B. And then player two also has two strategies, A and B. And then inside the matrix, right, you have pair of values, P1, P2. So it says if player one choose A, player two also choose A, then player one will get this P1 and player two will get this P2. Okay? And then if it's a zero-sum game, then P2 can be omitted, because whenever you have a P1, for example, P1 is 10, then this P2 will be minus 10, right? Because they always add up to 0, right? Okay, so I will give you some examples, which is the famous prisoner's dilemma. So in this example, you see there are two prisoners, and then well, some people is trying to interrogate, right? So two of them asking them, did you commit? Did you, well, so how to say? So now here in this example, it's kind of blame, right? So do you blame the other person? Okay, do you blame the other person? Okay, so everyone has two choices: blame or do not blame. So blame means the prisoner one says, okay, prisoner two, he did something bad. Okay, this is blame, right? He did something bad. You should you should hold him for a longer time, okay, in the prison. So this is blame, right? So you see, if every prisoner blame the other person, then the payoff will be this. Okay, so this is what this means, that player one will be sentenced to 10 years and player two will also be sentenced to 10 years. All right, because, well, both of you are guilty, right? So I just sentence you to 10 years each, right? Okay, now the other entry, this one means what? This one means prisoner one blame prisoner two. Okay, but prisoner two didn't blame prisoner one. So basically, prisoner two says, okay, prisoner one is innocent. He didn't do anything wrong. Now, of course, in that case, prisoner one will be released, right? He gets 0 years sentence. And then prisoner two, well, because prisoner one says he's guilty, well, okay, he will be sentenced to 20 years. Okay, now this is symmetric, right? If player two and player one's strategy is reversed, and then it will be prisoner one sentenced to 20 years and prisoner two sentenced to 0 years, right? Now the last one, both of them choose to be silent. Okay, one do not blame two, two also does not blame one. So in this case, it's not 0-0. Okay, because you know, the reason that they are in is that they are suspicious of doing something bad, right? So if both of them say, oh, the other one didn't do anything wrong, okay, now still the judge cannot believe in this. He said, okay, since we cannot find evidence, but still you are suspicious, right? So we'll sentence you each to 1 year only. Okay, so then why do we call this is a prisoner's dilemma? Okay, let's analyze a bit about this game. Okay, so in this game, you can see if we start from don't. Okay, we start from don't, because actually this is the best outcome, right? This is the best outcome for both of people, since the total sentence is only 2 years. It's a minimum. But this is not stable. This is not natural equilibrium. Why? Because you see, if both players' strategies do not blame the other, then player one will think, okay, can I deviate? Can I change my decision to blame? If I change my decision to blame, I get only 0 years. Well, my partner get 20, but I'm better, right? I get only 0, so I will deviate, right? Now, same story for player 2, right? So if you allow player 2 to move first, he will also deviate. He says, okay, why not? I blame him. Because then in this case, I get 0, he get 20. Okay, so basically this 1-1 is not stable at all. It's not natural equilibrium. But these two are also not natural equilibrium because you see, if you are at this stage, then prisoner 1 will say, okay, since you blame me, now I will blame you, right? I will blame you because, well, if I blame you, my sentence will reduce from 20 years to 10 years, right? You see, it's 20 to 10. It's an improvement. So I will do this, right? And the same story happened here. If you are here, then the status will also change to this strategy because player 2 will not be happy because now he gets 20 years. Now after changing his strategy to blame, he only gets 10, right? Get 10 years. So every arrow point to the final outcome, which is Nash equilibrium. And in this Nash equilibrium, it's a so-called non-cooperative equilibrium, right? Because these two players do not negotiate beforehand, right? And they just act on their own. If this is the case, the Nash equilibrium will lead them to 10-10, which is not the best outcome because the best outcome is 1-1, right? Okay. Yeah, so I would like to see whether everyone get the idea of prisoner's dilemma. Let me just issue the survey. So is the idea or explanation clear? Oh, great. Okay, so it's a consensus, right? It's very clear. Nice. Okay, so now we come to another type of game. It's non-zero game. It's called a chickens game. Okay, chickens game. Now his chicken is not quite chicken. Okay, it's not like a animal. Well, but the following name is really the animal name, hawk dove name. Okay, hawk dove game. All right. So what does it mean? It means that the two players, they want to fight each other. Okay, but they have decision to make whether they should fight or dodge. So this dodge corresponds to chicken, right? Because dodge means I'm not a I do not fight you. I do not fight you. I just hide from your attack, right? Okay. So basically, it says that when both players fight, their utility is negative 1,000. But basically, it's well in Chinese there is a famous idiom about that, but I guess I will not. I do not need to say it here. Everyone knows the meaning of the negative 1,000 and negative 1,000, right? And then if you see one of them fight, the other dodge, then the one fight will get +1, right? And then one dodge get -1. Okay. All right. And then similar story happened for this one. Now finally, if both of them dodge, they will lose nothing. Okay, 0-0. So this is a very famous non-zero sum game. All right. And then again, you can analyze the equilibrium here. So what's the equilibrium here? So some of you raised a comment about -1,000 and -800. Well, but I didn't get the meaning yet. So basically, let's follow the let's see what's the transition. Okay, if both of them dodge, you're here, right? Okay. So is this stable? Is this one stable? No, right? Oh, I see a yes, but many of you say no, right? So the reason no is that now one of them will say, okay, if you dodge, I should fight, right? Because if I fight, I get 1, right? I get 1. It's good for me, right? Now, same argument applies here, right? The other player will also try to change, right? Okay. Well, so now you are here, right? You're here. So are these two stable? Yeah. Okay. I see many no and also some yes. So it's no or yes. So actually, well, actually it's yes. Why? Because you see that these two are quite stable. Why? Oh, so oh, sorry. My fault. It's not stable. It's indeed not not. Let me just yeah. Okay. So basically, if you you change to this one, right? If you change to this one means player 1 will get +1, player 2 get -1, right? Okay, so for this, but you see, the reason is when you choose dodge, you gain, right? The one who choose fight will lose. So actually, my analysis just now seems not working, right? So these two arrows, are they correct? These two arrows, are they correct? If you dodge, will you change to fight? Yeah, because sometimes I would just like to see whether, yeah, okay, very good. Now you understand, right? There is no reason to fight, right? Okay, so basically this dodge, now these two arrows I draw here is misleading, right? They are not right. They are not right because if you are 0-0, if somebody change their strategy from dodge to fight, he or she will lose, right? Right? Because you see, change to fight, it becomes -1, right? So nobody will change. 0-0 is very stable, actually. It is a Nash equilibrium. All right? Nobody will unilaterally deviate to fight if the other one dodge, right? Okay? Okay. Yeah, it's not fight +1. It's a fight -1. Okay, so when you look at the payoff matrix, right? When you look at the payoff matrix, let me see my cursor. Where is it? Okay. So basically, when you choose fight, this is player 2, right? When you choose fight, you get this -1, right? It's not +1. +1, the first entry is for the role player. It's for this one, role player. Okay. So I'm giving you a some kind of a misleading analysis at the very beginning, right? Because well, you may think that fight will gain, but remember, even in a very famous real games, all right? So fighting games, when I dodge, I'll gain something, right? If you fight my dodge, you didn't hit me, but you waste your energy, right? Okay, yeah, so you are right. So this one is wrong. Very good. Okay, so that's the reason that some of you will have confusion, and this is also the the potential bug I embedded into my slides. Okay, so upper right should be -1 +1. Okay, yeah. So in this case, let me write down the name. Yeah. Okay, so this one should -1 +1, right? And then everything is settled. Okay. Let me see whether I have the most updated well, so the chat. Let's see. Yeah. So any question remaining about the chicken game? Yeah. So it's very good to be tentative. All right. So although the embedded bug is not many, sometimes it will be some surprise. Okay. So this is the chicken game, and then let's look at the very famous rock scissors paper game. And this game, I do not need to explain, right? Everyone knows. Okay, rock beat scissor, scissor beat paper, paper beat rock, right? Okay, and then when you have tie, the payoff is 0 because it's a regame, right? And then when rock beats scissor, the rock gets +1, right? And scissor gets what? -1. Okay, so this is a very, very, very well-known game. Now, in this game, can anyone tell me, is there a Nash equilibrium in this game? Oh no, right? Because no matter which one you play, the opponent can always find one better than you, right? Okay, so consensus again, right? Everyone knows that in this game there's no Nash equilibrium. Okay, good. Well, this is good. But on the other hand, this game later on we'll come back to it, although not picture-wise. Okay, so we'll come back to it because for now we only focus on pure strategy, which means everyone has a fixed strategy. But if we allow mixed strategy, then there's a different story. Okay, so we'll come to that very soon. And then there's also a so-called soccer's game. The soccer's games means that you have a shooter, you have a goalkeeper, and then the shooter will decide whether you shoot left or middle or right, and then the goalkeeper will decide to protect the left or protect middle or protect the right. Okay, so in this game, again, the payoff is very straightforward. When you choose the same direction, goalkeeper wins, right? And then if you choose different direction, the shooter wins. Well, that's again very straightforward. Now, is this one a zero-sum game? So I see many no's, right? I see many no's. By definition, it is indeed not zero-sum game. But yeah, so I see Ian said, and also some follow-up students said, yes. Okay, so actually it can be transformed to zero-sum game because every entry, right, add up to 1. So you just, for example, you can just decrease, right? Or you change 0, 1 to be negative 0.5 and positive 0.5 or negative 1 plus 1. Yeah, then it's just zero-sum game, right? So basically, the methodology we use will be following the zero-sum methodology. Okay, so this is another also very well-known example. Okay, so now we come to this. So before I come to this, actually Shinra asked if you change the score like this, then all non-zero game can be changed into zero-sum game. But actually, it's not quite because sometimes for some sum, well, so well, how to say that? In some scenarios, because in the previous one, in this one, it's easy change. It's just shifting. So it's just shifting. Basically, it does not change the structure of best response, right? But if you change it for arbitrary game, then it will change best response, and then or it will change the benefit or change the utility each one can get. Then the reasoning architect that framework will be totally different. Okay, but for this one, it's okay, right? We understand that by a slight same offset shifting, it becomes zero-sum game. Or maybe when we design it, we can also make the 0 to be -1, right? But there are multiple ways to handle this. Okay, so I hope I answered your question or concern. Yeah, so now we come to this mixed strategy. Just now we say rock, scissors, paper game, right? No Nash equilibrium. But there's some good news. So the good news is if we allow mixed strategy, which means it's a convex combination of pure strategy. All right. In other words, you can say, with a half probability, I use rock. With quarter probability, I use scissor. With another quarter probability, I use paper. So this can be a strategy. All right. And then you also have a best response. So given other agent strategy, what's the best combination of yours, right? And then Nash proves that for each non-cooperative game in normal form with a finite number of players, each having a finite set of strategies, there always exists a Nash equilibrium in mixed strategies. Okay, so here best response is defined in expectation. So can anyone guess what's the best or what's the Nash equilibrium in mixed strategy for rock, paper, scissors? Oh, very good. 1/3, 1/3 for each, right? So each one with 1/3 probability, that will be the best response or best mixed strategy for that rock, scissor, paper game. Okay? Yeah, so this somehow closes part of the Nash equilibrium study, and especially in normal form. Okay? Well, any question up to now? I believe that this part, right, as I promised, it will be much easier compared to the triangle one. Okay, and also, well, we will see more examples later on. Okay. Yeah. Okay. Well, so next category will be single play versus iterated game. So single play means I only play once. Iterated means you may repeat the same game, for a finite number of times. And also, there are some kind of infinite repeats of games, right? You can repeat it many, many times without limit. Now, for example, when you talk about prisoner's dilemma, then maybe there is no longer any dilemma, because imagine there are situations where the two people are in prison this time, and then if one of them blamed the other and the other one didn't blame, and then after 20 years, suppose they enter the prison again. Now at this time, the second player will not be choosing that strategy anymore, right? So you will somehow choose the other one, or maybe when they are out, they negotiate, right? So maybe let's just choose not to blame, right? Both choose not to blame. So basically, when you have infinite or finite repeats of games, there may be some negotiation happening, or there may be some retaliation, right? So if you blame me this time, then next time I'll blame you, right? So it's kind of more behavior will be involved in the gameplay. And then another thing is also very interesting, is called Bayesian game. And actually, this one, after finishing this one, I guess we'll take some break. Okay, so Bayesian game is what? So it's now before we talk about Bayesian game, we will first analyze the so-called Monty Hall problem. Okay, so now let me. So there are some comment here. I just want to know whether you know this problem or not. Okay, so let me post the questionnaire. So did you hear about this problem about the 3 doors? Okay, about 3 doors. You choose one at the beginning, and then in the middle, somebody will reveal an empty door for you, and then you will given the chance to switch your choice or not. Now, at the very beginning, so I see there quite some of you didn't hear about it. So let me just explain a bit about this problem. Okay, so there are 3 doors. So behind one of the door is a car. Okay, it's a very expensive car. And then behind the other 2 doors, there are goats. Okay, they're cheap goats. Okay, the other 2 doors are goats. And then you say, okay, but you don't know which door contains which object. So at the beginning, you randomly you choose one door. For example, you choose this door, and then the organizer says, okay, now I will reveal one door for you. That door is a goat. Okay, and then you are given a chance to switch your answer if you want. Okay, and then the question is, would you switch your choice? Now, of course, here you already see the answer, and many of you say it's yes, right? So now let me just ask one more question. Do you know why you always change your choice? Yes or no? Do you know the reason? Okay, many of you know. Okay, well, that's good. Well, so now it becomes half-half. Now, it has something to... Oh, okay. Now it becomes 40-60. Then I need to explain a bit. Okay, so it's not the major focus, but it's good to know. Now, why do we... okay, you say yes, but not quite agree. Well, now, let me show my understanding. Okay, now I believe that some of you have the same understanding as me. Although maybe I may also not agree, but well, it's a standard probability analysis. Okay, so let's see the reasoning. You have 1/3 probability choosing a car at the very beginning, right? Okay, and then if you choose the car at the beginning, and then you switch, then you lose, right? Okay, now this is the chance you lose. With 1/3 probability, you lose the car, although originally you get the car, right? Now, if originally you choose the goat, then the organizer will release the other goat, right? Okay, because he cannot release the door you chose, right? That's not fair, right? You cannot do that. So in the multi-hole problem, the chair will only release the one of the two remaining doors you didn't choose, right? Okay, so if you choose a goat, then the chair will release the other goat, and then you switch. That means you get a car, right? So you have 2/3 chance. Switch will give you the car instead. So basically, now I always changing. There are 2/3 probability you get the car eventually, right? 1/3 of probability you didn't get the car in the end. So that's good, right? Because you have more than half chance you get a car. So of course you will choose always to change, right? Okay, so this is the reasoning, the standard reasoning. Well, it's a bit non-standard. Well, it's a bit how to say, non-classic, but I guess this is fine. So, well, now my questionnaire next will be, now firstly, do you understand the argument? Oh, good. Majority understands, although a few do not. Well, but that's fine. But yeah, because anyway, there are quite some probability questions which are very, how to say, tricky. Although yeah, okay. So Wing Chong is helping me to answer the the question, right? Okay. Yeah. Now, yeah, there are two goats. Yes. Sorry, I didn't draw the third goat. Sorry. Yeah, this is also goat. Okay, there are two goats. Okay, right? So the chance you chose a goat in the very beginning is 2/3. If you chose a goat and then switching will give you the car, right? Because you chose a goat and then you know where the other goat is, then switching definitely give you the car, right? So, but although you don't know at the very beginning whether you chose the goat or not, but that doesn't matter, right? Anyway, your strategy is always switch. Okay. So if you chose a goat door, why switch to car? Okay. Well, remember, car is more expensive, right? Car is far more expensive than goat. So of course you would like to win the car instead of stay with the goat, right? Okay. So now I guess for this question we just why not switch to another goat? Because another goat is the door is opened. You know that where the other goat is. Okay, because yeah, so the chairman, right, will tell you, okay, I will open one door for you, all right, and in that door is a goat. All right. Okay, thank you. Now let's move on. I hope that I believe that more of you understand this point. Now, Bayesian-Nash equilibrium is what? The Bayesian-Nash equilibrium will be a strategy to maximize the expected gain of all players, depending on what each player believes about the strategy chosen by other players. Well, this is a bit abstract. Let me show you some example. So there are two things. So the first thing is not very serious. It says that the company A may not know the demand of its new product, and it also does not know whether company B will sell products of the same type. So he need to make some decision based on his understanding of other people, right? Okay, and then in chicken game, in the earlier version, it will be a pure strategy, right? Or mixed strategy, and then but now there is something new. All right, the original example about chicken game. So actually, you can also write the strategy to be there. All right, so this is a kind of fight and chicken. All right, so fall back. Right, so you can have payoff matrix like this, but in reality, the payoff matrix may be different based on different types of players. For example, if both players are aggressive, right? If both players are aggressive, let me show you the, okay? If both are aggressive, then the payoff matrix is like this. Okay, so this means what? It means, well, if they both fight, they get a -4. If one of them fight, the other one dodge, the dodge one get -2. Okay. Oh, this is a bit well, strange, right? Because well, the one who dodge get -2, the one who fight get 2, right? So in this case, it's a bit different, right? And then there's another case when P1 is aggressive, P2 is feeble or somehow weak or timid. Okay, and then the entry is different. You see, it's no longer 2 minus 2, it's 2, 0. Okay, which means the feeble one dodge, then he gets 0. He do not lose. He does not lose, right? And then if, for example, if or on the other hand, if the feeble one attack, he also does not get anything. All right. If the feeble one attack and then the aggressive one dodge, then the feeble one only gets 0. Not like this too. Okay. Well, so basically the message I would like to bring up is that based on different types of players, the payoff matrix may be different. Then what can you do? Then you need to guess or estimate what is the type of the other player, right? And then I need to make my decision or choose my strategy based on how he or she will do, right? Or what the payoff matrix look like for him or her, right? And that's a bit tricky, right? So now here is where the nature comes into play. All right. So we introduce the so-called third player called nature. Let me see. There's one question. Incomplete information. That means that I do not know which type the other player is. Okay. I know perfectly well about all the possible payoff matrix, but I do not know what is the other player's type. I know my own type. For example, I know I'm aggressive. Okay, I know this, but I don't know whether he is aggressive or not. Okay, then I have uncertainty. I don't know which payoff matrix I should follow. Right? Okay, so is it okay with the general idea? So basically, the incomplete information says, well, the other player, what his nature is, I don't know. Right? That's why I'm a bit hesitant about which strategy I should take. Okay, good. Okay, so now you see nature is playing a role. So what's nature's role? Nature's role says, okay, I am responsible for selecting the type of both of you. Okay, so basically there is a distribution function. Now every player has some distribution of which type it is, right? For example, for me, right, player 1, there is a 50% chance I being aggressive, 50% chance I being feeble, right? And for player 2, there may be 60% chance he's aggressive and 40% chance he is feeble, right? Okay, but how do you know which combination is really realized? Okay, well, so nature, okay, it will select the combination, okay, based on the distribution. Yeah, you're right. So basically, nature is just a kind of a I will select the distribution. Well, distribution is known. He is selecting the real implementation, real sampling of the distribution, right? Okay. So now you will continue playing the game, and then you see aggressive player 1. See, there's no questions. Okay, so Yao is asking maybe the player can learn other players' type from the payoff if the game is repeated. Well, if you consider repeated that game, yes, you can do this. But this time we are not doing repeated game. We are just doing single round game. Okay, so basically every player can compute his own utility. All right. For example, I'm using the earlier tables to do the computation. Now, for player 1, all right, player 1. Suppose P1 is the probability having an aggressive player 2. Okay, so I will multiply P1 to what? The gain I can get with aggressive player 2, right? And then, but again, there is some uncertainty, right? Because there's an X. So the probability for aggressive player 2 to choose you, complicated, right? So you need to mix these together, right? So basically U1 U becomes this value, right? Plus the probability of being feeble, and then you always get 2. Now basically you see that so we just look at one entry. Okay, so U1U, okay, U1U. So because P1 is the probability of have aggressive aggressive P2, then it means both aggressive, right? Both aggressive. So both aggressive. If you choose U, what will you gain? Now, if your opponent choose U, you get -4, right? -4. So that's the entry here, right? -4. -4 plot times X. X is the probability that aggressive player 2 choose U, right? And then another one, when will he get 2? When the other one choose D, right? Okay, so the probability to choose D for the other one is 1 minus X. So, well, okay, you have some calculation of this, right? And then you would do the same for the other one if the other player is not aggressive, right? Okay, so basically you can compute those utilities. And then, well, there are some complicated computation here, but for the purpose of the course, we'll not go into details. But if you are interested, you can dig deeper into how everyone computes its best strategy, right, with the knowledge of the other, right? But here, I'm only trying to say that based on the observation of yourself, you can estimate the probability of the other player based on the joint distribution. Okay, so this is the formula to calculate, but I will not go into the formula. I will just give you one example that's more easier to understand. So suppose I tell you the joint distribution of 2 aggressive is 0.2, and then player 1 being aggressive, player 2 being feeble is 0.3, and then the other side is 0.2, and then both feeble is 0.3. So I tell you the distribution of every combination, and then you will know if player 1 is aggressive, then what is his view on the other player? Okay, if he's aggressive, then you only need to worry about these 2 entries, right? So that means the nature is choosing something here. And then if nature is choosing something here, you will know that player 2 being aggressive on the condition that player 1 is aggressive is 0.4, right? Because 0.2 over 0.5 is 0.4. Okay, so after you know yourself, then you can estimate the probability of the other player being certain type, right? So 0.2 over 0.5 becomes 0.4, and then this one is the opposite, right? So when player 1 is aggressive, player 2 is feeble, it's just 1 minus 0.4, or 0.3 over 0.5, right? 0.6. So basically you can compute all these probabilities. Okay, so this nature, right, is being very fair. After it tells you what your type is, then you can compute the probability of the other player being this type or that type. That's very easy to compute. So basically the P here is very easy to compute, but there is still uncertainty about this X, right? So, but as I said, we'll skip the details here. You can explore by yourself about how to really compute the best strategy for Bayesian game. Okay, yeah. So the equilibrium, well, it's well defined, right? So everyone tries to maximize its expected gain when the decision set of the other player is given, right? Okay, so this is the thing, right? And then we'll take 5 minutes break again, and then come back to cooperative game, right? Okay. So meanwhile, feel free to ask questions. I'll take some water. Shushin is asking what's the relation between the triangle and the reduction. Are you talking about the Sperner's lemma? So basically, the Sperner's lemma, the triangle, Sperner's lemma says you can always, there is always a triangle with different labels on 3 corners. and then reduction is about end of line, right? So basically, it just says we can use Sperner's lemma to show there's always an end of line in the constructed graph, and uh, finding the end of line is difficult because in Sperner's lemma, finding that triangle is difficult. Okay, so this is the relationship between the triangle and reduction. Okay. Um, yeah, before we start, I would also like to know your opinion because, well, in this course, I'm trying to um, cover as many things as possible, although not everything is will be examined. So that's why I only give you 5 minutes break in the middle. So I'm just wondering whether it is okay to have 5 minutes or you would prefer 10 minutes between each session. So if you are good with 5 minutes, you can choose yes. So let me, if you are good with 5 minutes, then you choose yes. Otherwise, you choose no. Okay. Yeah. So we'll do a majority. So probably I will stick with the 5 minutes for now because so I will finish the poll and then yeah. So here is the result. So I understand that some of you may think it's too much, but well, it's fine because well, what I mean it's fine is that well, as I said, not everything will be tested. So, but when you know more, it definitely will help you in the future. So that's why I'm trying to cover more. And also, for your information, probably in the starting from next semester, the courses will all have 3 hours lecture, maybe. So, for this course, actually for graduate course, well, this is another issue, right, about the tutorial, because up to now we don't have any tutorials. So that matches the design of the graduate course. Actually, in the coming years, well, it will be the 3 hours lecture instead. So I hope that is fine with you. But of course, we'll arrange some sessions to explain questions if, well, when needed, right? Especially before midterm. So I'll arrange some sessions like that. So don't worry. Yeah, but of course, I can also be lazy to give 2 hours lecture this time without violating any rule. But well, again, I think for the benefit of all of you, I chose to, well, just use up all the 3 hours. I hope it's okay. Yeah. So yeah. So Wing Chun, yes, definitely. I will tell you when. Well, I will tell you when something is not examined. Yeah, yes, you're right. I will tell you, but well, at some time, of course, before the exam, maybe. Right. For now, I also not sure, but before the exam, most likely I will know. Right. Okay. Um. Yeah, I'm not sure about undergrad course. You may wait to see. I'm not very sure. Okay. Anyway, yeah, so let's begin. Now we come to the category of cooperative game versus non-cooperative. Now, the previous examples I show you, they are all non-cooperative games, which means that players, they act on their own, right? They do not negotiate, they do not coordinate. But sometimes there are some cooperative games, like the following game called Gloves Game. So Gloves Game, it's very easy. It says that there are three players. Player 1 and 2, they each hold a left glove, right? And player 3, it holds a right glove. Now, you know, for gloves, left and right, they somehow are, if you match them together, then they will be valuable, right? If you only have left glove, it's worthless, right? Okay, so now this is the definition, right? So the pair of gloves is worth 1, and then coalition means some group of people, they go together, right? So 1, 2, 3, 2, 3, 1, 3. So all 3 combinations, they will be good. They have value 1 because they have 1 left glove and 1 right glove at least. So all the other combinations will be 0. Now in cooperative game, there's a very famous value called sharply value. Now in the topic of cooperative game, we'll talk about it in more detail, but now I will just give you an impression about what sharply value is. Now the sharply value is trying to divide a total value of 1 to 3 players. And then you need to decide, okay, player 1, how much he should get, player 2, how much he should get, and player 3. Okay, so now the way to calculate here, you see S1, S2, they're both 1 over 6, and S3 is 2 over 3. So you may wonder, how do you have how do you arrive these values, right? Now I will show you the way. Okay, now X1, X2, X3, so they are the values or money allocated to each player, right? So they add up to 1. And then when we decide how much value, how much money you need to give to each player, then we'll need to compute the so-called marginal value of a player. See how much marginal value player 1 can bring to the whole community, right? Okay, so now we'll consider all the 6 arriving orders. What are the 6 arriving order? 1, 2, 3, right? 1, 3, 2, and so on. I will not write everything. Okay, so we have 6 arriving orders of the players, and among the 6, only 1, 3, 2, 3, 1, 2 will make player 1 valuable. Why? Because remember, 3 is holding a right glove, right? 1 is holding a left glove. So only if this 1 appear right after 3, then it will make a pair, right? So whenever you make a pair, you earn a value 1, right? Okay, so all the others useless. Why? Because, for example, let's look at 2, 1, 2, 3, 1. 2, 3, 1, remember, 2 has a left, 3 has a right. So up to now, they already get 1. When this one comes, no use, right? Okay, so you can verify all the other 4 sequences, right? Basically, 1 is useless, especially when 1 comes at the beginning, right? When 1 comes at the beginning, no use, right? It did not give you anything at that time. So that's why among the 6 sequences, only 1 sequence is good, right? Oh, then that means what? That means I'll give you 1 over 6 money. Okay, now symmetrically, because agent 2, the player 2, also has a left glove, right? So he will also be given 1 over 6 money. And then because sum is 1, so player 3 gets 2/3. Now, of course, you can also directly compute the player 3's 2/3 by going through the 6 sequences to see, oh, actually 4 of them will, the player 3 is contributing marginal value of 1. So I'll give you 4 shares out of 6. Okay, well, so this one, just do a survey. Is the explanation clear about Shapley value? So basically, he would need to decide, right, how much money you should give to each player, right? And then the way to do it is to go through all the possible arriving order, and then to see in each arriving order whether that player are contributing some marginal value. So yes, I guess someone is trying to ask questions. Is it? Maybe just accidental. Okay. Well, so now, of course, for those who didn't understand yet, we still have 2 lectures in the coming weeks to explain the cooperative game. So no worry, here is only kind of introductory. Oh, 1, 3, 2. So Jiangpeng is asking why 132 1 is not valuable. Okay, so the reason 132, yeah, so you answer the question, right? So in that case, 3 is valuable because when 1 comes, you only have 1 left glove. So at that moment, no value at all, right? And only after 3 comes, 3 will make the whole thing complete, and 3 will contribute a marginal value of 1. So did I answer your question? Or you answer your question? So basically, marginal value means when you arrive, right? What's your added value on top of the earlier total value? Okay, right? Okay. Well, so of course I'm being a bit fast here, but no worry. This part we will revisit in some later lectures. All right. So remember marginal value, right? Marginal value means the extra value added towards their earlier group's value. Okay, not future, earlier. Okay, so now we move on. Okay, now there is another game called Stackelberg game or leader follower game. So this game is also a very famous game. So basically in this game, it's also kind of two-player game usually, and the leader will announce some value, right? And then the followers will play the game with the value specified by the leader. And for different values, the game will achieve different equilibrium. And then the question is, how should the leader select the value? Now, here, the reason that we have the so-called followers, so YS, because sometimes it's played in among multiple players, all right? So you can consider a scenario called crowdsourcing, right? I have a task, and then I will distribute the task to many, many people. So please help me to complete the task. But then I need to tell them how much money I will give to everyone, to all of them, right? So then the leader will decide, I will give $100 to all of you. So then you can decide how to play the game, right? And of course, every player, they try to maximize his own gain, right? So with a different budget, they will behave differently, of course. So the leader tries to get the most benefit out of the whole game. So he needs to decide on a budget, right? So this is the setting for crowdsourcing. Now, there is also easier explanation about the two-player game, right? This is much, much easier. So in the two-player game or normal form game here in the payoff matrix, now suppose leader is player 1, okay? The player 1 will say, okay, I will decide one row, okay? I don't know which row. I will decide first row or second row. And then after player 1 decide the row, the follower or the player 2 will observe the commitment and then chooses a column. Okay, so if I choose the first one, right, and then player 2 definitely will choose here, right? Okay, because he has 1, right? Now if player 1 choose this one, then player 2 will choose what? Yeah, it will choose the right, right? Yes, very good. Okay, so now player 2 will choose this, right? Oh, sorry, here, right? Because this one is larger than this 0. Okay, so now the question is, which row does player 1 choose? Okay, I see many of you answering second. Okay. Yeah. Okay, so the reason you choose second, right? Because if you choose second, then since player 2 choose this one, so player 1 can get utility 3, right? Okay. Now if player 1 choose first, then we already know that player 2 will choose the first column, he gets this, and then player 1 can only get 2. So between 2 and 3, of course, he will go in favor of 3, right? Okay. Well, so this is the explanation about the Stackelberg when it happens in normal form game. All right. Now here, you do not need to worry about Nash equilibrium anymore because there's a commit from player 1. Player 1 says, okay, I will choose row 2. So player 2, please play. All right. Okay. So even though in Nash equilibrium definition, somebody can still deviate, that's fine. That's fine. I don't care. All right. Because you see, the only deviation comes from this direction, right? But this direction is not possible because player one already committed some decision, right? Okay. So this is Stackelberg game. But of course, Stackelberg game by itself, it's much richer, right, than this. I'm trying to give you an example, showing the idea about leader and follower. All right. Okay. Yeah. So let's then move on. So now we will come to some very interesting application examples and some paradoxes. And this part is, well, very interesting too. Now, we first go to some paradox. Now, here is the shortest path auctions. What does it mean? Now, the scenario is the following. You have a buyer, and the buyer wants to purchase a path from S to T in a graph. All right? And then in the graph, every edge is owned by selfish agents. Okay? If you want to purchase a path, you have to purchase every edge on the path, right? So you need to pay the agent some money who owns that edge. Okay? Now, edge costs, they are private. So only the agents know the true costs. And then what we try to do is we want to lower the buyer's expected payments in the shortest path auction. Okay? Okay. So now, one possible solution is the following. So every edge, they can submit their bids, and then that buyer will choose the cheapest path. Okay? And what's the payment? So here, payment is a bit tricky. It says the payment will be paying each winning agent its threshold bid. Okay. Well, what does it mean? Well, in order to explain this, I'll first explain the auction. All right. So it's only very brief explanation of auction. So in auction theory, you have one item, and different buyer has different value towards the item. Okay. So for example, the first buyer think, okay, this item is worth $100. Then the second buyer says, okay, I think it's worth $50. Okay, and so on. Okay, smaller and smaller. Okay, now if you want to make sure nobody will cheat on their true valuation, then we need to adopt a so-called second price auction, which means the one who gives the highest bid will get the item, but he only pays the second bid in the list. Okay, why do we need to do this? Well, if you ask the first bidder to pay $100, then the first bidder will think, okay, maybe I'll do some survey to see how low I can report, while at the same time I can still get the item. So the 100 may think, okay, I bid 51. Okay, then the item is still mine, right? And now I pay only $51, right? So it gives the bidder some incentive to cheat on its true valuation. That will make the whole thing too complicated, right? So we would rather only charge the top bidder $50. Okay, I will charge you $50. Then you will not have any incentive to cheat on your bid. Why? Because it's useless, right? Because, well, you can imagine if you cheat to be above 50, no difference, right? You still pay 50, so it's not worth it. So if you say, I cheat to be below 50, will that be good? If I cheat to be below 50, will that be good? No, right? The reason is, well, if you cheat below 50, you lose the item, right? 50 gets the item. You will lose it. So if you lose it, you will be very sad because, well, earlier I can use $50 to buy an item which I think is worth $100, right? So if I lose it, then I lose the extra gain of 50. That's not worth it, right? Okay? So that's why people use second price auction, charging the winner only the second price below it, right? So you have top price 100, second price 50. So I only charge you 50. I will not be very aggressive or greedy, okay? I only charge you 50 to make sure you will not cheat me, right? You do not have incentive to cheat me. Okay. Well, so this is the reasoning about second price auction. Okay, so is it clear about the arguing about well, if you use a second price auction, then no, the winner will not have in incentive to lie. Okay, so there are someone who didn't get it yet, but well, I guess it's fine. Anyway, it's not a major focus yet, so can still take some time to think about it. Well, but one thing I missed. All right, so just now I said that no, the so, or in other words, I'm trying to explain the green words, right? Truthful. That means people will tell the truth. But did I finish the proof? Did I? Did I finish the proof? Showing that nobody will cheat about his valuation, about his idea about well, how valuable this item is to him or her. Did I finish the proof? So yeah, still thinking. Well, it takes unusually long. So actually, it's a bonus question I planned. Um, but I think that probably well because well for many of you it's the first time you well get into the auction thing, so probably it's not that easy. So maybe I will tell you the answer. So actually, I didn't finish the proof. So which part am I missing? It's still a question. It's still a bonus question. I didn't finish the whole proof. I'm missing something, right? I proved something, but I missed something. Only if you add that thing, then the whole proof will be complete. So what do I need to add? Yeah, the agents are non-cooperative. Yes, you're right. Threshold bid may not be true. Avoid high cost. What's the task? Oh, the task definition is you need to prove that nobody in the system, in the bidders, has any incentive to report a wrong information or a false bid. For example, if he thinks the item is worth $50, he will not cheat to be 30, right? So basically something like this. Oh, actually, the whole thing, one thing is not shown to you, right? So I didn't tell you what everyone's utility is, right? Because everyone is trying to maximize its utility. So utility is the value minus the price he need to pay to the system if he gets the item. If you didn't get the item, the utility will be 0. Okay. Yeah, rationality. So everyone tries to maximize his or her utility, right? Well, I guess this one is really a bit tricky. So let me tell you. So then you will know. Wow, which part am I missing? Just now I showed you the winner does not have any incentive to report a wrong value, right? But is that enough? You also need to show that the loser. Others we don't care. Well, we care, right? You also need to make sure the others will not misreport, right? Okay, so that's why we also need to show for the losers, they do not have an incentive to misreport. Okay, why? Because for a loser, if he misreport below 100, he will not get that. So no effect, right? If he misreport to be above 100, he will get the item, right? He will get the item. But in that case, his net gain or utility will be a negative value because he will pay 100, but he only thinks the item is worth $50, right? So it's a negative gain. That's not good, right? So for the loser, he will also not cheat. So the loser's argument is a bit different from winner, because loser, you need to argue for overbidding. But winner, the major thing happens in underbidding, right? Okay, but anyway, as I said, this is not major focus. The major focus is now you are clear. For the winner, you need to pay, or he needs to pay the so-called threshold payment. Okay, so this is the value below which, if he reports to a value below that, he will lose the item. That's not good, right? Okay, so you just ask him to pay that value, right? Okay. Well, so now let's look at one example about the threshold bid. Okay. The example is here, all right? Well, the intuition is here, all right? So let's look at example first. So in this example, we have many edges with zero cost, okay? Zero cost. And then you have one edge costs one edge is cost 1. Okay, so remember our algorithm is to ask them to report, right? And then I will choose the shortest path. So in this example, the shortest path is 0 0 0 0 0, right? So this path length is 0, and I will pay each of them some money, right? Okay, so because we are trying to avoid misreport, so we need to pay each of them 1. Because if, for example, I pay him only 0.1, say, and then this edge says, okay, I will misreport. I will say my cost is 0.9. You will still choose this path, but then I will receive 0.9, right? So at least you need to pay the one I claim, right? At least the one I claim. So if you pay any edge below 1, that edge will have incentive to increase his bid to ask you to pay more, right? So because, well, every edge can increase his bid to 1 or to be very close to 1 so that the top path is still selected, right? Okay, so that means for each such edge, you need to pay it $1, $1, $1, right? But you see, you have many such edges, so you need to pay M dollars in total. But what's your best solution? The best solution, just pay $1 and choose the bottom path, right? Okay, so that seems that asking all the people to report their cost and then pay them so-called threshold payment is very inefficient, because well, it's very far beyond the optimal cost. Okay, all right, now we come to the intuition. So here we're thinking, well, can we do some changes on the graph? For example, can we add new edges in the graph? Well, probably adding new edges is not possible, because you see the edges are owned by agents. So how can you create a new edge from scratch, right? Nobody owns that edge and they create a new edge. That seems not possible unless you are doing some kind of fake creation of the agent, right? That's not good. But removing edges can be performed by prohibiting some edges or some agents from participating in your game, right? So there is some counterintuitive observation, which is also a kind of paradox. If we remove an edge, which means we forbid someone joining the game, okay? I tell somebody, okay, you cannot join the game. Now, this means we are reducing the competition, right? There are less people competing. Usually, if there are less people competing, you have to pay more, right? Because more competition means the buyer, they can buy cheaper things, right? But now you have less people competing. Supposedly, you should pay more. But actually, in our case, it's not. Okay, we are paying less. Why we are paying less? Let's look at the picture again. Suppose we forbid this edge. Okay, we forbid this edge. Oh, please do not join. Okay, and then the only 2 valid paths is the bottom 2, right? This one and this one, right? Okay, well, then I will choose any one of them. I only need to pay him $1. Why? Because, well, $1 is the threshold payment. Any one of them, they cannot increase their bid to be higher than 1. If they increase to be higher than 1, I will choose the other person, right? I will choose the other one cheaper than you, right? So basically, this competition will help the buyer to secure a payment only $1, right, to get a path from S to T. So you see, by removing an edge, actually you gain, right? The buyer can pay less to get the shortest path. Okay, so this is about the shortest path auction. Okay, so next, I will talk about some classifications of Nash equilibrium. All right. So earlier we mentioned that in a game, sometimes there may not exist any Nash equilibrium, and sometimes Nash equilibrium will exist, right? But not every path converges to Nash equilibrium. In other words, when you go along the so-called best response cycle, right? So see, one improves his utility, and then two improves his, and then move on. Okay, if you move on, you enter some cycle, then you will no longer be able to reach Nash equilibrium, right? Okay, so here I will just try to model the Nash equilibrium computation as a graph. In this graph, every node is a what? Is a state of strategies from all players. Okay, so every node is a possible combination of strategies. And then between nodes, you can have links. So this link means one player moves to a better strategy given other strategies fixed. Okay, so basically this is either a best response move, or later on you will see something like a better response move. Okay, so basically somebody is trying to improve his own benefit. So if you are able to improve your own benefit, I give you an arrow, right? Okay, so now your this graph have some arrows, right? And then we are trying to say, okay, Nash equilibrium is a node with no edges going out, right? Only incoming edges, right? Because Nash equilibrium is stable, nobody will move. So nobody will move. That means no edges going out, because that's edges mean that somebody will gain, right? Okay, so no edges going out. The sink in the graph will be Nash equilibrium. But our task is to find the Nash equilibrium. That's very challenging because the number of nodes in the graph is exponential. Okay, it's not polynomial. So, well, the only way or only effective way is to follow the arrows, right? Follow the arrows, and at some moment we expect to reach some sink where no edges going out. Then you find Nash equilibrium. But well, if you have a cycle in the graph, so if you have a cycle, then you may just follow the cycle always, right? No ending. Okay. So if you have a cycle like this, right, and then you may say, oh, player one improves, player two improves, player three improves, player four improves. Oh, then cycle. Player one improves, two improves, three improves, four improves. Well, that's no end for the computation. So that's not good, right? Okay. Now, there's also another category of the Nash equilibrium where the equilibrium exists and every path converges to a Nash equilibrium. This is the best possible scenario for computing Nash equilibrium. And then in this case, actually, we can design the so-called potential function, right? And this potential function will help us in this scenario. So actually, potential function, we will also cover it in the remaining material of the previous lecture. So we have some potential function method. So later on, when we revisit that part, you'll be have more idea about what potential function is. So basically, potential function in general means what? Means that when you go along different edges, right, from node to node, make sure that whenever you follow the edge to a new place, there's a function. So there's a function on the node in the graph. Okay, there are function. So if there's an edge from u to v, then we make sure fu is always larger than fv. Okay, so this is a if and only if. Okay, so if there's an edge from u to v, then fu is larger than equal to fv. Now all the f are larger than 0. Okay, all the f are larger than 0. All the f u of v is larger than 0. So this is a potential function. So potential function means that when you follow the arrows, it's just like your potential becomes lower and lower. So just like a ball, earlier you have a large potential value, and if the ball rolls down a slope close to the ground, the potential becomes lower, right? Okay, so this process just tells you if you follow the link, it's just like the ball rolling down the slope, and then gradually, well, it will go to some bottom, right? If you go to some bottom, it's very stable. It's that Nash equilibrium. Okay, so that's another way to understand Nash equilibrium. If you have a potential function for that game, it's like you draw, you slide right to the very bottom, and then now it becomes stable, right? Okay, so this is about potential function, and actually there is a um, very good example which we will systematically introduce a bit later. So in this game, it's called total distance game. All right. In the total distance game, there are n players. They are playing on a graph with n vertices, and each of them will choose one vertex. So strategy is just choosing one vertex. And now what's the agent's or player's utility? So utility is his total distance to all the other players. So basically, I, as a player, want to be far away from other people. Okay? Okay, so you can see that when, let me see the, okay. So when there are people here, right? There are people here, 3 people here. Now, if I'm here, then I will see, should I move to the other node? Okay, I will calculate the distance, right? This one plus this one plus this one, my current total distance to the other 3 nodes. And then to see, well, if I move to a new direction, a new node, I moved here, then what's my total distance to these 3 nodes? All right. If the new destination has a larger total distance, then I will move. Okay. So this is what the agent will do. Each agent will do. Okay. So again, polling. Are you clear about what agents can do in this game? And what's the well, we are trying to compute the Nash equilibrium, of course, right? Okay, very good. The majority of you understand the setting. Okay, then let's see. So now, let me ask, any limit on how far they can go? Okay, they can only go to a node. No limit about the distance they can travel. So they can move from one node to any other node. They cannot communicate. Yeah, so this is a non-cooperative game. Can they choose the same node? The answer is yes. They can choose the same node. Okay. All right. Then I guess after addressing this question, many of you already know what the game is, right? And now I have one question. Is this game a potential game? In other words, will every move by any agent improve some function? Or so by the way, potential game, the function f, which we defined earlier, you see this one, right? I said that fu larger than fv if u can go to v, and fv larger than 0, but actually you can also do the reverse. It's also okay as long as the one direction, it's okay. Okay, Wing Chun said that they can keep looping, right? Spinning means looping. Okay. So any different opinion? Is it a potential, or is there any loop? Yeah. So in other words, is there any loop in the when people try to improve their distance to the others from the others? Remember, only if you strictly improve your distance, you will move. If it's tied, you will not move. All right. Okay. So Xuejun said that every iteration, everyone's distance does not decrease. Okay. So that means actually the total distance this value. Oh, not the same time. Okay, one after the other. Okay, so you're asking a very good question. These players, every step, only one player will move. Okay, you can choose anyone to move. Will there be a loop? So, Ziel, are you saying that in this case, the answer is yes, there will be a loop? Oh, it's a potential game. Good. Okay. So, yeah. So the answer is it is a potential game. All right. Well, why? Okay. So actually, just like Xuezhen said, right? So actually, Xuezhen, so right. So as both of you noticed, in every move, the distance from one agent to so Xuezhen, it's a not yet totally uh, correct. Okay. Uh, so the point is, in every round, all right, in every round, one agent moves, then his distance towards the others, this one increases, right? That's the reason he moves, right? That's the reason he moves. His distance, his summation of distance to all the other people, it increases. And now the distance between the other people, did it change? No, right? It doesn't change. So overall, the total distance between any pair of players, this total distance will increase, right? Because mutual distance between the non-moving agents, they didn't change, but the distance from the moving agent to the non-moving agent, it increases. So overall distance, right? The total sum increases. Therefore, every move, the total distance will increase. And that's can be the potential function we design, right? So this potential function is a beginning of certain value. Every time you move, it becomes higher. Every time you move, higher, right? But well, you have a finite number of states. So every time you become higher, eventually you will stop at some moment. When you stop, that means you cannot be even higher, right? Okay, then it's just the Nash equilibrium, right? By using this kind of potential argument, then you find the Nash equilibrium, right? Okay, so I hope that by using this example, you have a better understanding about the potential function, right? So you try to argue certain quantity will only move in one direction when your agent improve their utility, right? Either it increases or it decreases. Anyway, in one direction, in any direction, consistently, that would be good. All right. Okay. So now we move on to the next one. The next one is again a paradox. It's a very interesting paradox. I like this example very well. Okay, so what's this paradox? So the paradox has a name, but I didn't put the name here. You're encouraged to find it. So basically, it's trying to say how bad is selfish routing. Okay. So what is this? So it's basically about phenomena which we may observe in real life. So suppose we have one new highway built. Okay. Now, according to our common sense, with a new highway, usually the traffic congestion will somehow be alleviated or be softened or reduced, right? But the fact is, usually you have one new highway, it may worsen the whole situation of the traffic. Okay, so this is a paradox. All right, supposedly adding one new free highway, it will be very good, right? But actually it's not. Well, let's see how to argue that contradictory argument. Okay, so in this example, you see on the left, this figure, no highway, right? There's no highway. And no highway, you have 4 roads, and this L function is called latency. So latency means when you have X cars on the edge, then every car needs to spend X time before you can reach the next node. So basically, the more cars on the road, the more delay it will be caused for the car to travel, right? So this one, I guess you agree. And then we have 4 edges. The first edge, the delay is proportional to the number of cars. And then the second edge, the delay is constant. No matter how many cars, the delay is always 1, which means it's kind of okay, kind of very spacious. Okay, no no extra traffic or extra burden will be caused, right? Okay, and then you also have one edge like this, symmetric, and one edge delay is x. Yeah. Okay, so now if you want to route 1 unit of traffic to the destination, then what would you do? Yeah, so Chengyu, you are right. The paradox name. Okay, so this one, you see, if your x is 1, the whole traffic, we normalize it to be 1. Okay, we normalize it to be 1. Then what do you see? And then you see everyone's selfish, right? Everyone wants to have shorter delay. So you can imagine half will be a very good solution, right? So half traffic go up, half traffic go down. In this solution, the delay of every direction is just a 1.5. Do you agree? Because the delay on the first edge here is half, and the second edge is delay is 1, right? So 0.5 plus 1 is 1.5. Below is also 1 plus 0.5 is 1.5. Now, in this solution, nobody will deviate. For example, for those who chose the bottom path, he will not go up, because if he go up, he increases the load here, right? And then his delay will be more than half. It becomes 1.551, 52, right? That's not good for him. So basically, the two groups of people, they are evenly distributed. They just choose their own way. Everybody has delay 1.5, and nobody is willing to go to the other one, because if it goes to other one, it brings extra burden to the other pass, and the delay becomes larger than 1.5, which is not good for him, right? Okay, so this solution, actually, well, nobody will deviate. It's a Nash equilibrium, right? It's an equilibrium based on selfish routing. Now, so I will pose a question. It's okay about this explanation about why half of the traffic choose the upper and half of the traffic choose the lower. Okay, yeah. Majority understands. Still some didn't understand. Well, if you didn't understand, you we may spend some time offline to get it. Yeah, so we'll finish this and finish today's session too. Now, let's look at what happens when you have an extra highway whose delay is what? 0, which means it's super fast, right? No delay. Okay, will that be good? Well, let's see. Earlier we say one group 0.5, you choose this one, right? Upper pass. And one pass 0.5, you choose the lower pass. Okay, right? Is it stable? With this extra highway, it is no longer stable. Why? Okay. You see, well, this one, right? The upper half one, it says, I need to suffer a delay of 1 by following the second path. But if I somehow deviate like this, then I only have an increment of delay 0.5, because the bottom path only have 0.5. So basically, if I follow this detour, I only need to suffer a delay of 0.5. So of course, it's better for me. And then for the upper path, they will just go this way, right? Instead of going upper, right? They will go first upper, and then through the highway, and then go through the lower edge. And this move will continue until all of them are here. Okay? So, is it good? Right? So basically, at the beginning, this new path gives them delay of total delay of 1, which is better than 1.5, right? And then with more and more people coming in, the delay is still 1, because the total traffic adds up to 1. So when you have less people here, right? Less people. Oh, sorry, it's not still 1. So this is a half, right? This is half. So if your half all come here, it becomes 1.5 eventually. Okay, so at the very beginning, if very few people moves, then it's kind of a good improvement, right? But when more and more people move, then the improvement becomes less and less important. Okay, so eventually the stable state will be the upper group will go up and down and then up. Okay, like this. Now, just one, yeah. So this is the first detour, right? But is this stable? Now you see you have. Let me see. Is it stable? I see many no's. Okay, it's still not stable. Well, that's interesting. Okay, why it's not stable? You see, this edge is suffering a delay of 1, right? Okay, then the lower group will say, huh, I can make a detour. I can go up first and then down. And this will only give me a delay of 0.5 at the very beginning. Okay, so when very few people move, deviate, it only give me a delay of 0.5, which is better than 1, right? Okay, then of course we will deviate, right? We'll choose that path. So all of them, all these x, all the half, they will choose to first go up and down and up. So basically, eventually, all the people will choose this one, right? All the people choose this one. This is the final stable state. Now, this one actually is very bad. What's the delay of this one in the end? Yeah, very good. The delay is 2, right? Well, you see, without the highway, delay is 1.5. With the highway, the delay becomes 2. It's totally because of selfish routing, right? Okay, now just one last comment. Okay, the last comment is maybe some of you didn't understand because we say x is 1. Well, I need to explain one thing. So actually, this is only normalization. X is 1, but you can consider each car, individual car, is a very tiny point of x, which means it can be 0.000001. Okay, it's a very, very tiny car. So basically, it's possible that there is a very tiny car changing from this path to that path. So that explains why the x can gradually decrease, not like a sudden change. Okay, yeah, you're right. So you're right. So 1 just means 100%. Yeah. Okay, so I guess today I will just stop here, and then next week we'll continue along this topic. All right. So any question? And also, I would like to have one more poll. So overall, before you answer, please listen to my question. Overall, do you think that this lecture is easier compared to earlier lectures? Okay, so I see a majority chose easier. Yeah, so basically for game theory topic, I think it would be useful for you to know the different types of games, because in your future research or in future job, you may need to model your own problem as a game problem and try to design some solution for that. Okay, so in the end of the slide, we will explain the potential approaches you can follow to design such things, to design and solve games. All right, but not yet. We'll cover that in the coming lecture. Okay. Okay. Yeah. So now question time, and feel free. Okay. Agree. Agree that beginning slides about concepts is a bit hard. Well. Well. I see. For those who disagree, well, definitely after the lecture needs to spend quite some time. That's something for certain, all right? Because not every concept or every example can be understood by everyone. That's basically not possible. So if you didn't catch something, then you need to review after class. And I know that the load in this sense will be heavy. This is something true. But you know that heavy load will mean more gain. That's also true, and I hope that you agree with this. And for the exam, well, you will see how difficult the midterm will be. Um, well, I will not make the exam hard. Um, just try to, well, okay. So um, now there's one question about the midterm, whether it will include questions about explaining these concepts. Um, Explaining concepts is the least ideal question I will ever make. Uh, but these probably will be the easiest question if you are good at uh, knowing those concepts or differentiate those concepts. Um, more ideal types of questions, they will be uh, well. So for example, I can give you one example of midterm questions. So I would prefer to see more calculation or deduction questions. So one possible question, actually, you can also guess, is that I give you a payoff matrix. You need to find me a Nash equilibrium. Would you think that question to be difficult? So like this, right? I give you a matrix. I ask you to find an equilibrium, or I ask you whether a certain state is equilibrium or not. Uh, a bit hard? No. Uh, so I mean, well, just like this one, right? Okay. Yeah. So basically, I would expect, for example, um, um, that if I give you a 2 by 2 matrix telling you the payoff of each player of each of the two strategies, then you should be able to compute or decide whether a certain strategy combination is a Nash equilibrium or not. Okay, so this is a decent question. All right, so I would think this question is on the easy side. Okay, yeah. So I agree with you, Shen Yuan. So more parts on game theory. Oh, okay. Well, Yuan Hang, you are raising a very good point. So you're basically asking whether this question will be worth only 2 points or more, right? So if it's 2 points, then it will be difficult. Yeah, agree. Okay. So this type of question in the midterm, I think it will be worth at least five. Okay, maybe up to 10 points. Oh, oh, okay. So one question is about whether it can recommend you some materials for further reading. Uh, so um, so there are some books on game theory. Um, I'm not sure whether so there is but that book is a bit hard. So there are books on game theory. If it's not on the syllabus, I will try to find one which is more on the fundamental level, and then so that you can have a better feeling about the different knowledges, right? Okay, so yeah, algorithmic game theory. That book is okay. It's good, but as I said, that book is more research based, so probably it will be very so especially the later chapters will be very challenging. But earlier chapters that may be fine. Okay, so the algorithmic game theory book, it, as far as I know, the first eight chapters are fine. They are basic knowledge, but still, it is more for research. So, in general, it is still on the intermediate to high level. There may be some other books on game theory which is easier. I will explore some. But if you think that you can handle that book too, then it will be fine. And then Xiao is asking are the proof tricks in approximation algorithms required. So the proof tricks, okay, so how to say, I'm not intending to test you on those very difficult tricks. And also NP complete, I will never test you because it's not our focus. And then so the most likely question will be, now you may consider, oh, by the way, I released the assignment, you see, and actually you could consider the assignment on bean packing to be the right level of questions I may ask in the midterm. So basically, um, uh, it will be some kind of a easy startup. There will be simple cases first, and then gradually becomes a bit more general. So let me see. Yeah. I believe so. So if this last question in assignment 1 is worth 25 points, yes, I totally agree with this suggestion. Yeah. So basically, even if I test you some new questions, I will give the description very clearly, and then it will be possible, not possible, probable that majority of you can follow those steps one by one, and I will not require sophisticated techniques of online algorithm analysis or approximation algorithm analysis. That would be too much for exam. All right, for assignment maybe it's okay, but for exam, no. Okay. Um, oh, okay. So in class exercise, the you, so Zheng Yan told me that the Canvas deadline is February 27. Then it's just February 27. Okay. So because up to now, all the questions you already know from last week. So actually, I believe that it's reasonable to finish within this week. Okay. Oh, okay. So it's about the last question in tutorial 1, right? So the last question, uh, uh, okay. So oh yeah. So sorry, I apologize for that. That yeah, it's because we postponed the lecture by 1 week. So supposedly we should postpone everything by 1 week. So yeah, I agree. I will adjust the deadline to be next week instead of this week. Yeah. Okay. And then okay, so there are two more questions. One is for assignment 1, there is no submit entrance. I will check it very soon. And then there is also a question on the last question in assignment 1. So sorry. Oh no, in class, right? The last question in class exercise, tutorial 1, right? In tutorial 1. So the expectation of the answer is an algorithm. Okay, algorithm which can generate the optimal solution, and you need to prove that it can really generate the optimal solution. So this is the expectation of the answer. And then given order, let me just see whether Canvas has recovered now. Yeah. Oh, the given order is just an arbitrary given order. Okay, so basically, given order means that you specify a priority among the nodes. So basically, that order just tells you the priority, and then if they differ as the original order, then you will count it as reverse. Okay, so that is just an input. Okay, so there is another question. If you select OJ assignment, you only need to choose one more assignment. Well, so I remember we say that the OJ is worth one assignment. Is it right? So I have the impression that either one or two, right? Oh, I said two? Okay. Okay, yeah. So in that case, you can, it's equivalent to two assignments. Yes, you're right. You're right. And then Jian Cong asked me for 1, 2, 4, 5, 3. Is it true that there's only one reverse, 5, 3? Yes, you are right. And yes, so let me see the question. If you solve all the 5 OJ tasks, you just have to do one more assignment. This is correct. And then uh, if you finish OJ 5 question and some marks are deducted from the later 3 assignments, can they be complemented by OJs? Well, these are separate, which means that OJ are OJ, all right, and then assignment is assignment. So if you choose to use OJ, and then assignment, you can only pick one. You can only pick one, which means if you even if you do two, they cannot match each other. So they cannot um, put some marks on the other to make it a whole. So that's not that does not work. Yeah, pick the highest is okay. You're right. You choose some components. I will pick the highest 3 components, and OJ is counted as 2 components. Okay. Yeah. Any other questions? Okay. One more question. Since you asked, can you explain the relation between PPID and spinal lemma? Okay. Let me stop sharing first. Okay. Oh, I didn't realize that when I switch to full screen, it becomes this. Yeah. So Spinner's lemma is uh, about the existence of a triangle with all 3 labels, right? And then the lemma is used to prove this problem, end of line problem, is hard. Okay, and then um, about PPAD complete. Uh, so it just means that in the in all the problems which can be solved if this end of line can be solved in the category. So it's kind of like the so PPAD is just like MP, and PPAD complete is MP complete. It somehow like MP complete. So PPAD complete problems, they are the hardest problem in the PPAD category. Okay, so and then Spinner's lemma is used to show that or at least or it's used to build a connection between the triangle thing and the end of line problem. Okay, so basically these two is considered to be the same difficulty. Yes, I just see a new comment. Page 50. So did I answer your question? Okay, good. For tutorial one, do you need to answer code, pseudocode, or text description? Uh, it's actually for tutorial one, you only need to use text description. You don't need to give me codes. Yeah. Okay. Okay. Great. Then if there are no further questions, then see you next week. And next week, I guess I will start with the remaining part of the game theory basics, and probably will cover the remaining part of the algorithm part, and then we'll start the cooperative game. Okay. Yeah. Thank you. See you. Bye.